microphone.
Hello. Yes. So after tendering my apologies, I'm starting this talk, which is, I don't know, maybe the title itself is not matching with that what I'm present here, but that's what it is. Longitudinal advantage of middle class telescopes for transients, including, of course, Sampurnanand telescope. So, as we all know, that India lies in the middle of 12 hours of gap of longitude and could play crucial role towards study of new transients coming up, including GRBs and many others. As we know that we are right here, and as you can see that still, since GRBs were discovered, the clustering of these optical infrared facilities have not changed much since then. So this longitudinal advantage is the crucial thing. And this is a time era of multi-messenger time domain astronomy. We will be talking more, but here is a very old plot, has been populated now much. But if you see the decay time scale and the absolute magnitude, then GRBs, which are for the subject today, are lying here, and many other transients. So there's a big question mark where it is very clear that due to sensitivity limitation or our own technological limitations, it is defined as known unknowns. Means if these all areas are populated, then this area should also have some sort of population. And why they're not there is the known unknown. So this known unknown phase is the era of future, with all mega projects coming up and with all LIGO and all non-electromagnetic spectrum, what we are aiming mainly, this area is supposed to be populated soon. Again, coming back to longitudinal advantage for India, we all know about these slides. So around same longitude, as you can see, we have many facilities, and we are right here, and many other telescopes are also functioning in the country. And when we started our activities long back, let me rather, sorry. Oh, you AP direction में जा रहा है. I think yesterday also this problem was there.
Forward, backward. Backward नीचे है. ये pointing on.
No. Okay. All right. Yeah. So with this longitudinal advantage, the subject of today, that is the GRBs, gamma ray bursts. So we all know, and the gentry sitting here is quite aware about this subject. So the one point I would like to highlight here is the extremely large distances and energy. And in news also, last week there was a GRB 1009, and this has broken all the records, and it is so bright in gamma rays and X-rays that most of space-based and ground-based detectors, they got saturated, including LAT. So that was at a 0.15 redshift, and it was extremely bright, and it is going to challenge all possible theoretical models which have been in fashion as of today. So we will come there. But meanwhile, in last couple of decades, we also knew that not only supernovae, but kilonovae are also associated with some of the GRBs. At the moment, it is hard to say whether kilonovae are associated with just short duration GRBs and supernovae are associated with just long duration GRBs. This myth is going to be challenged, and it has been already challenged, in fact. And that's what is the subject of today, that the bimodal distribution, which was long back, was thought that the duration distribution is something like that in gamma rays, there are short and hard population, and here is the long and soft population. is no more exists. And probably that's where the GRB research is going to be focused in future. And why we say always GRBs? Why not other very scientifically much more productive subject areas? For example, star formation and AGMs and galaxies, which are kind of scientifically more yielding, and they're telling more about universe rather than just transient events, is following. Because this subject area have a very large multidisciplinary coverage, including that ultra-relativistic particle acceleration physics, which is least known, how the heavy element synthesis came, and how elemental abundances in fact evolved in the universe. Because when we study stars, then we study about normal elements. After hydrogen, helium, lithium, carbon burning, we understand that that's how things are evolving. But once it comes to heavy nucleosynthesis, R process and S process, then it's very hard to understand from normal main sequence stars that that just cannot be understood. But if we take catastrophic events and talk about non-thermal events and synchrotron and inverse content and relativistic outflow, then definitely we have some clue to understand that what's all going on. So that's how this subject area is important. Dense matter, dark matter, cosmology. If we talk about observational cosmology, then also because up to 10 redshift, and we are expecting to go 20 redshift soon with the mega census coming up, maybe up to 30 redshift. So GRB is being very intense for the main sources. So if we want to understand high redshift universe, then apart from galaxies and infrared bright objects and galaxies, transients are other sources which are of crucial importance. And as I emphasized with R and S process and that how actually elements came into existence and how they are synthesized is the atomic, nuclear, and astroparticle physics. So with these kind of high impact areas, that's how transients and particularly GRBs are important. Going back to some historical remarks, here is the very first GRB, 670702. So as all of you probably know, YYMMDD. So we are talking about 67. And that's when Sampurnanand telescope was conceived, project 67, 68. And at around the same time, because it was a Vela satellite and for nuclear test ban treaty, different US and USSR, they launched and they, instead of getting terrestrial, they got celestial. And since then it was a kind of secret thing, and later it was 73, it was announced, and so on due to many political reasons. But this and it took, as you can see, 67 and 97. So it took another 30 years to come to other electromagnetic spectrum part and say that here are the afterglows and measure distances and so on. As you can see that without optical localization, which is basically sub-Oxygen localization, because the high energy photons, be it LAT or MEB or KEB, I mean, the point spread function is larger. The effective area was smaller since very beginning. So when collecting effective area was smaller, the point spread function and sensitivity and detector, all those things were unable to localize at the level of arcsecond. So it was just not possible. In 97, it happened. And attempts were started to monitor afterglows with 104 Sampurnanand telescope early on. So before 97, it was not possible. So in 98, so please correct me if I'm wrong. Alokji gave me a CD where in 98 also we attempted one afterglow and one field was captured. And
that I can tell you.
Yeah.
At that time, it was for calibration.
But one field was observed.
No,
Yes.
but that's not for GRB afterglow data. It was for the calibration of the field.
So it was taken a few days after the burst, maybe a month after the burst. But as rightly pointed out, that we in fact were on the job from 98 itself, that these are the enigmatic sources and these are energetic sources and so on. And so that's where credit goes to Sampurnanand telescope that it has started activities. And somehow I have lost that CD. Very bad.
Can't we
Ji.
No, she has published.
Yeah. Oh, I'm sorry, it is 10 minutes. Sorry, sir.
Yeah, probably same.
Yeah, so, oh, it's already 10 minutes. So coming back to short duration GRB, the situation now is that different class of photometers and the binary neutron star merger and the neutron star black hole merger may create prompt emission afterglow and dynamical ejecta interacting with the interstellar matter and surrounding matter may create situation after the afterglow. You could have a red kilonova, blue kilonova, and so on, several possibilities, and from all the way from GW to neutrino to radio, on what time scale it is possible to observe are written here. And similarly, in long duration GRBs also, now we more or less understand that it's a hydrogen star, Wolf-Rayet star, and if the jet bored through the center of the star, may it be neutron star or a black hole, and it bores through the star, and if the jet is coming out nicely, then it may create a very well-defined jet, and the observer is sitting on axis. He or she may be able to see the afterglow part. And there are cases where if the photometer is taken, not just the WR star, but maybe some yellow supergiant or blue supergiant, like that, or if not, then even due to some reason, if there is an extended mass envelope, and from core, if the relativistic Lorentz factor 100 stuffs are coming out, maybe the baryon dominated or magnetized outflow, they may not be able to break through the stellar cocoon nicely. And it is not defined in terms of a very clean jet, relativistic synchrotron dominated, but shock breakout kind of situation may happen. And that's what may lead to low luminosity GRBs or supernovae like the hydrogen strip 1C, 1B supernovae or broadline 1C supernovae and so on. So prompt emission, we have reached well ahead. As you can see here, that BAT had a low sensitivity, and after 2008, we have GBM and LAT. So the prompt emission spectrum, this is basically, and as you can see in the BAT era, it was not possible to, the peak, that is the when the prompt emission spectrum is peaking. But now we know due to LAT and GBM, and not only we know E peak, we also know that the prompt emission spectrum is probably not going to be a very much empirical function like bands, but it may associate it with something like the broken power law, what we have in case of afterglows. So now people have started thinking that is there a single model where all the way from prompt emission to afterglows to very late afterglows, if it could be explained in terms of a situation like this, where in the oh my God, yeah, where in a situation where the pre-burst and at this time is scale and this radius, and then the burst and then the afterglow. So afterglow spectrum, which is the energy distribution of injected electrons, are now, since TeV GRBs are also known, at least 6 of them are known by now. So we understand that it is not only the electron spectrum, but it may be the proton spectrum also may be dominant at those energies. And if not synchrotron, then those synchrotron electrons may be boosted by factor of 1,000 or something like that, and may produce synchrotron self-Compton or inverse Compton photons and so on. So we are trying to trace back this kind of spectral energy distribution and trying to see if not only the afterglow phase, but also in the prompt emission phase, if this with this Lorentz factor and deaccelerating with time decaying. So is it possible to understand in a single unified model? Because GRB field will be, it's possible to understand only when, if we are able to explain at least part of it in a systematic single model fashion, because we know that hundreds of models have been suggested, but none of them have failure. So early afterglows are important, as you can see that in optical, depending on the resolution and so on, we are dominated by power law. It may have been features, but since our exposure time and all are limited with the sensitivity and the technology that we have, so we get something like this. In prompt emission, we get somewhat different features. So these are internal shocks, external shocks, progenitor model, underlying physical mechanism, geometry of the afterglow. So those are the aspects which are important. If you see the early afterglow property, this is X-ray. I am just focusing for the optical. So you see here the 1820 magnitude. As you can see, here's the zoo of afterglow light curves and R band. So 1 meter telescope plays role up to here. So as you see, in case of my point is that still the meter class telescopes are extremely useful to study objects like this. It depends that how effectively we are able to use it. If we are at the right place at the right time, then meter class, it's a game of meter class telescopes. Because all other telescopes are definitely having very large funding. Because of large funding, they're extremely costly, and many other science goals are there. So always disturbing others and saying that, hey, give me some time because I have to observe afterglow is not a very good strategy. And that's how you can see that it is important. And then early afterglows on similar time scale optical light curve decays differently than X-ray, and then late time central engine activity, physical mechanism, afterglow, and then 50% of GRBs are also very dark. Maybe they are host obscured, maybe they are intrinsically dim, maybe they are high redshift and so on. We don't know. And then all other things are also important. And whether jet, we are sitting right in front of the jet, or we are sitting off axis, or how the energy is distributed throughout the jet. It all depends on model that what kind of light curve would be observed and so on. That's how meter class telescopes are important. Coming back, that what we did, as you can see here, we started our activity 990123 was the first GRB where afterglows were observed, and this telescope was in line light that we discovered. Not discovered, but we followed up the afterglow. And as Professor Ramsagarji was mentioning, that from pager and from all other different kind of instruments, we were getting information, not like WhatsApp and email was not very common. So pointing out the telescope and blindly, in 99 and 98, it was extremely difficult. And and at that times also, around the day after the burst, we were able to contribute. So as you can see, this wiggles and bumps in the light curve, the main block. So the longitudinal advantage means if you don't get, you miss that, then you may misinterpret them as a simple power law, and then may not be able to tell you the characteristics behind those kind of events. So that's how the meter class telescopes importance are there. And as you can see that this paper, which was published by us in 2002, because of our data, we were able to say that there was no fake, and it was all a single power law, and it decayed very fast, and it was optically faint burst, decayed by 10 magnitude in a day, and at that time it was a big thing. And then we came in a collaboration era where at that time, apart from Professor Ramsagarji, Dr. Vijay Mohan, I would also acknowledge Dr. C.S.S. Stalin. And I was a PhD student at that time, and he helped a lot. And while writing one paper, Professor Ramsagar, led by Professor Ramsagar, it was a micro lens, GRB, and there were wiggles in the light curve which we observed. And then Professor Ramsagarji asked that for making modeling. And being a second year PhD student, it was not possible for me to do. So Dr. C.S.S. Stalin, one of the working mediums, he helped a lot, modeled for me, and that's how that paper was published. So Stalin and his memoir also, he has mentioned a lot about all those things. So the initial days were fantastically good, and it was a good learning and so on. Thanks to all who helped to establish this field right here for 1 meter class telescope. And then we collaborated with HCT during this commissioning phase. And as you can see that our data point is lying here. Just by using optical data, we are able to determine the jet plane. So in the absence of X-ray and radio, because it's supposed to be an achromatic break, so claiming just based on the optical UVBI data is quite risky. But we did it, and later on it turned out to be good, correct. So those kind of things also came out. And then later on came era with 03, 0329 kind of objects, which you can see that we were sitting in the dome, and suddenly the information came, and I moved the telescope, and the object was so bright that it was not, we were unable to believe that whether it's afterglow. So we did not send any GCN circular. But soon after, we got a GCN circular saying that here is afterglow, and that's how we missed the discovering the afterglow. And as you can see, the data points which we gathered with the meter class telescope, enormous. See? That CT and Sampurnanand telescope, blue data. So lots and lots of data, and this was possible to see the sideways expansion, and it was explained that the jet break would be there and so on. And the spectroscopy was not there, so I'm not going to touch it. So the bottom line is that where are we today? So in 2013, we were here, and more or less similar is the situation. That is short duration GRB and long duration GRB and low luminosity GRB and the T90 distribution. You see there is the overlap. And if you see the LISO, and if you see some empirical relations like Amati, then you will see that long following a different trend and then the short, and there are some outliers also now. So it's hard to say that whether the empirical relations are unified, and then they have to be incorporated in the models produced by different theoreticians. And if they are also correctly reproduced, then only we can say that the model is correct. If it is not reproduced, then it's very hard to say that the model produced by any theoretical ground is correct for the GRB observed particular. So I would like to emphasize for one GRB, which is 200826, and as you can see, the large error bar, 2 degrees. Am I right? Yeah, 2 degrees, GBM error bar. And then JETF kind of instruments, localized after referring to many objects, and then the T90 was 0.65 seconds. And all of the properties were also like, see the distribution, it was lying between long and short. And later on, when it was observed, then here is projected supernova model, and here is the afterglow. So it all indicates that being a short duration GRB, it was all underlying supernova. So that was first instance when it was challenged, and 3.6 meter DOT with 10 spec saw the host galaxy, and we modeled, and we were able to derive parameters for this burst. So what we are claiming is that 40% of LGRBs are misclassified as SGRBs, an indication to rethink over the rate of such age. So this GRB compelled us to think about current understanding about the physical mechanism. Recently, last year we got one more GRB at a very nearby, and one of the closest. It was at this redshift, and if you put it at redshift 1, then it would have been observed as a long duration burst only. But what happened? We got a chance to monitor the object with a 3.6 meter also. As you can see here, the 3.6 meter DOT, and then HST did not see anything at that point. And why I'm emphasizing it, you may ask that why are you talking about 3.6 meter and the telescope for 1 meter? So why I'm saying the answer is right here. See the bright. So my point is that if you are well equipped, then it's all meter class game. And this is the groundbreaking object, apart from what has happened just the last week. And my point is that we were at the right time, at the right place. If our aperture would have been just 1 meter, then also it was possible to see the object. And where we have come now in 2022, you can see the solid lines are the overall model. The dashed lines are the afterglow, and the shaded region is the kilonova. And you can see the non-thermal power law superimposed with the thermal axis emission talking about kilonova. So a very long duration GRB associated with the kilonova is the subject area. So that's where we have reached that the long duration GRB with the kilonova and short duration GRB with the supernova. So this is the classification challenge. And if you summarize the property, then you will see that here is the duration and the fluence and the lag and softer spectrum versus harder spectrum. So all the properties what we knew so far are it has all ups and downs, and it is all upside down. So it's very hard to believe what we learned so far, and we need to think that these recent cases clearly demonstrate that standard classification of GRBs are required to be relooked and carefully using both prompt emission and early follow-up data, and discovering new transients. This is important to understand, and meter class telescopes could play a big role into it. Thank you very much. I'm sorry.
Okay, thanks. Proceed for nice talk. One quick question, somebody can ask. Okay.
This gap between the short and long term bursts is filling up, are you saying that?
Not filling up, sir, but the point is that we need to understand the proposed theoretical models to understand the way they were classified are required to be relooked, number one. And it's more or less my personal assessment is that because of the limited sensitivity of the space-based instruments and so on, we actually misclassified them. Maybe some of the long ones were short and some of the short ones were long. So because of the lack of temporal coverage and because of the lack of lot of high energy coverage, some of them were misunderstood. And maybe with coming era and with coming days and with DW and neutrinos coming up, we will be able to understand them better.
Okay, Joshi, last
question. How about redshift information for the GRBs?
Which GRBs?
For GRBs.
Well, sir, I think by now some maybe 4,000 or 5,000 GRBs have been localized. For 1,000 of them, it has been redshift. For around 500 of them, redshift have been measured. I mean, the spectroscopy.
That's important.
Yeah.
That was important.
Okay.
Photometric.
Yeah.
Okay. Can you ask?
No, no.
Okay.
Yeah, I will come to you. Sure.
Okay, let us thank Sasi again. And next talk is by
Look at it.
Morning, everyone. So this is 2023. I started my research at Aries in 2002. So I'm celebrating my 20 years of association with Aries, although in between I was not here for a couple of years. But my association with ST also goes back about 20 years now. So I'm very thankful for this opportunity to discuss about some of the research work that we've been doing for the last several years. And also to Shashi for laying the platform for the transient astronomy program at Aries. And he has, in a very nice and a precise way, described about the gamma ray burst follow-up observations over the last several years and how this program started at Aries. I will be mostly focusing on supernovae and some other kind of transients because of the shortage of time. So moving on, the first mentor in this program, Professor Ramsagar, who initiated and established this program at Aries, and our mentor, Professor Dipankar Bhattacharya, without whom initiating this program would not have been possible. And as Professor Ramsagar mentioned in his inaugural talk on the first day, that Dr. Brijesh Kumar also moved into the time domain astronomy group, although he does a lot of other things as well. So Shashi and myself were the first PhD students in the time domain astronomy group. Initiating the program is an important step in starting the follow-up observations, performing the modeling and doing several other things. But sustaining the program is the most important aspect of any astrophysical research that we have to carry out. And that sustaining is possible only because of the young PhD students that we've been inculcating in our group for the last couple of years. And we're very happy actually to note the dedication that these young students have put in running this program successfully. Because transient astronomy is a program which requires dedicated follow-up observations. Unless you have follow-up observations, not even the theoretical aspects would not be proven to be right. So we really, really appreciate the effort of all these young PhD students who have worked in areas in the past and who are presently working in our group. So our tryst with supernovae with the 1 meter telescope started with the observations of SN 2002 AP, which Shashi has studied in great detail in his thesis. This is a very well studied broadline type 1DC, 1C supernova. It has very broad features in the spectra, which indicates very high velocities. And these velocities, these supernovae are very energetic. Until date, this is one of the best studied broadline 1C supernova in this category. So the early observations in Feb and March 2002 were taken with the Aries Sampurnanand telescope. Due to the monsoon period, there were no observations in this period, but HCT was in the commissioning phase that time. And in August 2002, the further observations were taken when HCT was still being commissioned. So this light curve you see over here, this beautiful light curve covering the rise and the fall of the light curve in the different bands of SN 2002 AP has been observed with the Sampurnanand telescope. Again, to emphasize the quality of the data that we've got over here. And these late time observations, these points over here have been taken with the 2 meter HCT. And with these observations, the decay of the supernova, as well as the amount of nickel synthesized in the explosion, were estimated because the peak coverage was excellent over here in all these bands. The first type 1A supernova, which we studied with the Sampurnanand telescope, was 2004 S. This was the first object which I ever studied as a transient source apart from GRBs. This is the image which is taken with the Sampurnanand telescope. Again, this beautifully well sampled light curve with the Sampurnanand telescope. And for this, we were able to, using all this multiband data, we were able to establish the bolometric light curve, as well as estimate the properties of the progenitor. And one important thing that we did over here is that using the color curves, we were able to establish the amount of reddening that the supernova host galaxy suffers, because reddening is a very important factor to estimate the absolute magnitude of the source. And using these color curves, we were able to do that. The first type 2P supernova studied solely with the 1 meter Sampurnanand telescope is SN 2004 ET. This is also a part of my PhD thesis. Look at the light curve over here, the rise, the plateau phase in the type 2 supernova, and the late time decay. So the late time one I have also zoomed out over here. Even at the late times, we were able to sample the light curve quite well. Fortunately, when I was working on this supernova, I just came across the Chandra archive and noticed that there were some Chandra observations available for this event. And because Chandra data was public, I used this data and studied the evolution of this supernova in the 0.2 to 10 keV X-ray bands. And we also requested for a GMRT DDT trigger at that time. And we got one observation at the 1.4 gigahertz with GMRT at the radio bands. So this is one supernova which has observations available across the different wavelengths of the electromagnetic spectrum. And because of the availability of such good quality data, we were able to constrain the mass loss suffered by the progenitor star, the mass of the progenitor, as well as the nickel synthesized during the explosion of this event. In this supernova, we also established the contribution of the different filters towards the bolometric light curve. We emphasized on the fact that why at early times the UV-V observations are important, because if you look at early times, the contribution from the U and the V bands is quite high as compared to the other optical bands. So which is why the early observations in the UV bands are very crucial, because they would contribute the most towards the bolometric luminosity. Whereas at late times, this contribution goes down, and at late times, even if you only have V, R, and I observations, we will be able to estimate to a certain level of accuracy the bolometric flux. So this was the first time that we had shown this in our paper, that why UV observations are important, and the same the same figure and the same approach we've used in several of our observing proposals requesting for multiband observations. This supernova was not studied with the Sampurnanand telescope, but this was observed with the HCT during the commissioning phase. And I used this HCT data from the commissioning phase and studied this type 1A supernova called 2003 HX. Why I would like to bring this supernova over here is that because you can look at the field of the supernova here, and the supernova is deeply embedded inside the host galaxy. One is just not able to see where the supernova is located. So a very, very accurate template subtraction technique is required in order to identify the supernova and estimate the true magnitude. So here is the subtracted image of this supernova. So at that time, template imaging had just started, and we were new to the image subtraction technique. This is the first event on which I performed the image subtraction technique. And the same concept we are still following for even the newer algorithms that we are developing for the ILMT now. This again was observed completely with the Himalayan Chandra telescope, and the supernova was very well observed. And because time domain astronomy was just starting at that point of time, so we were not very clear on how many observations would be sufficient. So during the commissioning phase with HCT, only 4 spectra were taken for this supernova. Whereas over time, we have realized that why a time sequence of spectroscopic observations is required to disentangle the different spectroscopic features that we see in a supernova spectrum. Shashi in his talk showed a slide about the phase space of these cosmic transients, and he also mentioned that there has been a lot of new discoveries, especially in this time regime, at the low, where the characteristic timescales are quite less, and the peak magnitudes or the peak luminosities vary. So the transient astronomy is no longer limited to gamma ray bursts or supernovae. There has been a complete zoo of transients which have been detected, especially with more and more survey telescopes coming up. The surveys being more and more sensitive now, we've been able to hit the transient space in a very good manner, and there have been several known unknowns that we are trying to address. And some of our observations have played a crucial role in studying these unknown transits, especially the core collapse supernova shock breakout. We've also been doing the tidal disruption events. We've been following the kilonovae, gamma ray bursts we've already been doing, and over here. So there are some transients over here which we are trying to, the properties of which we are trying to address, mainly because the location of the telescopes, the longitudinal advantage was very well explained by Shashi, and also because of the availability of these telescopes, which is why such a program is very well suited for meter class telescopes. So, yeah, the traditional classification no longer holds, which is also clear from the previous figure that more and more transients have added to the diversity of the events, and that is what we are trying to address. So our approach at Aries here is to study these transients which are detected by the several ongoing surveys. There have been surge of transients in the last several years. So we try to exploit the capabilities of the moderate size optical telescope at Aries in collaboration with several other worldwide telescopes available in the network. This is a simple pie chart of all the different types of supernovae that we've observed with Aries. Mainly the core collapse supernovae of the type 2, because they are more abundant in nature, they are discovered more frequently, as compared to the other rare class of objects, mainly the type 1bn supernovae, the type 2n. These are very rare class of objects, so the percentage is reflected over here. There are 2 main regions in the light curve which require emphasis. One is the early time light curve, because the rise is quite rapid, so you really need to catch these transients very early on in time, and the late time, because the late time observations sometimes are not possible because of the meter class telescopes, but still a 4 meter class telescope can do an excellent job in tracing the late time light curve of these supernovae. So these two are the less explored windows in the light curve of any transient event, I would say. And we need to put more focus on these 2 regimes. So we identify these supernovae, And we try to pick the transients which are relatively bright, of course, within the observational limitations of these telescopes. And bright in the sense that typically between 15 to 16 magnitudes, so that they can be followed for a typically longer period of time, like 6 months time scale. The spectroscopy can be done with the 2-meter Himalayan Chandra telescope or the 3.6 meter DOT. The 3.6 meter DOT, we are aiming at the nebular spectrum of these kind of events. The cadence is decided upon the brightness of the event that we are following up. It's the observations are at a high cadence at early times, when the cadence reduces towards a weekly, bi-weekly time scales at later phases. And for any event, we perform a comprehensive analysis in order to estimate the explosion properties as well as the progenitor properties. So this is a rare class of type 1AS supernova 2014 DT. The image taken with the Sampurnanand telescope with HCT and the 3.6 meter DOT. So we can see from this figure that the 1 meter image is at par with the 2 meter and the 3.6 meter DOT. Another interesting class of events, the transitional type 2B supernovae, where the early time features are similar to a 1D supernova, which later on transition to the type 2 supernovae. So even for these transitional class of objects, one needs to have a regularly sample light curve as well as spectroscopy in order to identify these characteristics also. So in the last several years, we've co-located the different classes of the type 2 supernovae in this diagram over here. These are some well-studied type 2 supernovae, which are at different brightness levels. And with this, we've tried to establish the link between the type 2 linear and the type 2P, the plateau supernovae. Again, emphasizing that why well-sampled light curves are important. In order to estimate the properties of the progenitor, we can also use the nebular phase modeling, the spectrum obtained at a nebular epoch beyond 150 days after the explosion. Once you model that, you will be able to get an idea about the mass of the progenitor, which has given rise to this, to any supernova. However, in direct imaging, the identified progenitors of the type 2 supernovae have been quite rare. Only about 2 dozens of progenitors have been identified, which are mostly the red supergiant kind of objects. But in observational studies, there has been a non-detection of progenitors with masses greater than 18 solar masses. But there are stars which are greater than 18 solar masses also. So this is popularly known as the red supergiant problem that we've had missing red supergiants in the observational progenitor identification of the type 2 supernova. But this is in contrast to what we see in the spectrum. In the spectrum, if there is a massive progenitor, one would expect to see a strong oxygen line. But in one of our event that we studied, 2015 BA, the one which is at the bottom, we did not find the presence of any oxygen line over here. However, with indirect methods, we established that the progenitor was around 25 solar masses for this object. So these two things are in contradiction to each other. So there are such known, unknown questions and features that we've been seeing in all of these transients, and hence it is important to study each of these in individual transients in detail. With AstroSat UVIT also, we've attempted observing the type 2 supernovae. This is a galaxy image of the field, and this is the UVIT image of SN 2017 EAW, where we were able to detect the supernova at a magnitude of 17.35. The key highlights of this program have been that the monitoring of transients, in particular supernovae with these telescopes, has been exceedingly useful to characterize the progenitor and the explosion properties. And the successively increasing number of supernovae observed. Detection is one thing, but the follow-up observations, which require a dedicated observational effort, has certainly allowed for a better understanding of the different types of different subtypes of supernovae, because as I said, that there is no clear demarcation between the type 2 between the type 1 and the type 2 supernovae so far. There's a whole variety of supernovae in between. And through this program, we've addressed some of the important points like the circumstellar interaction, which is seen in supernovae, the interplay of the stripped envelope and the interacting supernovae. We've identified the central engines, whether they could be the magnetars, or the progenitors could be the Wolf-Rayet stars, or even the LBVs for the interacting supernovae. The collective properties of supernovae will be very useful in addressing the stellar evolutionary theories in future. So our goal and our plan in the near future is to make available the light curves and the spectra of the supernovae which have been observed with the Aries facility to the community, so that the students can work on these light curves and do short time projects with that this data, and populating the phase space diagram of the transients. Because with the increasing number of surveys over the last several years, there are a lot of transients which are totally unknown. So with dedicated observational efforts, the space diagrams of transients has to be populated. As most of you are aware that we've achieved the first light of ILMT, and we are in the preparation for the second observing run of ILMT. Because it is a survey, and the potential of any survey is to detect and discover many new transients, and that is what we are expecting with ILMT also. But in order to do so, a clear transient detection and an alert stream is extremely necessary. So we're working towards this. But even after the detection, there has to be a follow-up of these transients, not only from ILMT, but the transient alerts which are coming from other surveys also. And for this, support would be required from other observational facilities like the 3.6 meter DOT and the Himalayan Chandra telescope. So our wish list, we've achieved this with the 1 meter class telescopes so far, but to push it one step ahead and to be in the game, it is extremely necessary that we have a dedicated transient monitoring facility, typically a 2 meter class telescope, which is equipped with a FOST-like instrument. Because even though when you are discovering the transients, the follow-up effort requires observational time on other facilities, which may be oversubscribed with other programs also. But because this is such a high yielding program, if there is a dedicated observational facility, we will be able to have more well-sampled light curves, more events, and particularly the spectroscopy, where we are at present, because 3.6 meter is heavily oversubscribed. So even for a classification program, getting early time spectrum is very, very crucial. So with bigger facilities, it's always not possible to just request a trigger to classify. But if there is an alert stream, which we will be sending out, so a moderate sized telescope with a FOST-like instrument would be the need of the hour in the next couple of years. So with this, I would like to thank the organizers for giving me an opportunity to present this work over here.
Right. Thanks, Kuntal. So question?
Very quick, suppose that you want to do a continuous dedicated monitoring survey and for this year. How the assessing survey program was that going to
Assassin is a targeted survey.
so
So we are not doing a survey because ILMT is anyway a
but
survey.
how that going to help you in collecting the information about ongoing supernova transients? So are you using that data also?
Assassin sends out transient alerts.
Okay.
That is a dedicated survey, and also it's a targeted survey looking at nearby galaxies. So when it sends out the alerts, they also perform the classification. And when if the object is of interest for us, it lies within the observational limitations of the telescope, then we would pick it up and start the follow-up. So Assassin would stop there itself. I mean, it just sends out the alert. But ILMT is completely different. ILMT is no way similar to Assassin over here.
One thing I can add that all the supernovas which are getting detected,
and not always classified.
Yes.
So that is one of the problem. I will show it in my slide. So that's why classification surveys. I mean, if you take it as this way, for that kind of survey, this kind of first-like instrument, dedicated instrument for that, and in the northern hemisphere is extremely important. For example, we know that there is an instrument like this in the southern hemisphere, and ISO, but the northern it is so far it is not.
No,
only
not
not
only that,
in-
even with the 2.5 meter this entity, the PESTO survey also
That is
runs. It's in the southern hemisphere.
it's a-
The
if it-
Chicago telescope,
Yeah.
the 1.82 meter, where they also run the classification program, have a cost-like instrument.
Okay, next question.
So is the time now right for national effort? Because I know that the VBO team, the team at IAA also follows up on, you also follow, and between the teams you have different sizes of telescopes of different locations. So is this time right for you to plan for the national supernova survey?
Absolutely.
Yes.
I would expand it out a little bit more.
So that
Not,
might be one of the options today.
not only supernova, actually, it can be any monitoring program like AGNs. I mean, because
No,
in
but this
supernova,
needs
we-
a long time of follow-up.
no, but in supernova, what happens is that we really don't need the entire night.
Yeah.
So
But you need
even
over-
if we are monitoring 10 supernovae over one night, there'll be sufficient time left for other monitoring programs also. So, I mean, that is absolutely the need of the hour, and I mean, we should plan for one such facility.
One more thing is
Uh,
coordination is
Maybe
required.
somebody else.
Okay, I think we are running out of time, so Stalin and Joshi, lot of questions. Okay,
Yeah,
so we can have after at the tea break, we can have this. So next talk will be by Rupak on recent trends in supernova research.
So thank you once again. After a long time, I am standing here. Thank you. And the third person did the PhD in transients after Shashi and Kuntal. Slide. So which is forward, backward, complete. Okay, so my main emphasis will be what is the recent. Okay. So my main emphasis will be what is the recent development in the supernova science. And I will mainly talk about what we can do with the small telescope, that is meter class telescope, and what people are doing throughout the world with meter class telescopes. So let us start with this, as in the previous speaker said, that about supernovas. Therefore, the supernovas can happen. This is a plot made by Hager in 2003 on the basis of stellar evolutionary theory, and it has been shown that the initial masses of the star and its metallicity distributions, and where the supernovas can happen, this is the different kind of supernovas can happen, and this is the what will be the remnants. So this is one-to-one correlations. So these are the regions where the type 2p supernovas will happen and which will produce the neutron star. There are then there will be type 1bc supernovas, and they will form may form a black hole or may form a neutron star as well. And there are other regions where massive stars will collapse and may form a black hole or may form an exotic supernova events. That means that supernovas can happen at any metallicity. But all kind of supernovas will not be same depending on the metallicity. we will get the different kind of supernovas. So as it has been shown in this figure, in the right hand side. So this is a schematic diagram of a galaxies. This is sort of edge-on view, and you can see that these red stars are basically the supernovas, and we can see that the supernova can happen at anywhere. And there are more interesting things are happening also very near to the center of the galaxies. Sometimes it is happening as a supernova, which I am saying it as a nuclear events, or nuclear supernovas, which are happening at the circumnuclear disk of the galaxies. And very near to the center of the galaxies, there are sometimes the stars, sun-like stars, can be disrupted by that by the massive gravity of the SMBH itself, and gives some sort of explosions known as the tidal disruption events, and which is equally energetic like supernovas. There are other events which happens at the center of the galaxies, like microlensings or changing quasars, etc. But I'm not going in those at this moment. We are now mainly concentrating on these transients like supernovas and a little bit on the tidal disruption events. So going back to the same plot, but in terms of energetics, and this plot has been shown by both Kuntal and Shashi. So this is the areas. So this is some hard bound in the mass range, which is the lower bound, below which we do not expect there will be a supernova, but there may be supernova of some other way, like neutron-star merger and those things. But if we consider a single massive stars, it cannot be done before this mass limit. So similarly, here also we have a bound in decay time and also in terms of energetics. So this is the region where we used to see the most of the energetic events about which we are talking now. So these are the other core collapse supernovas, and we are mainly talk on that. And I will not be talking on the type 1As and luminous supernovas and the tidal disruption events. I will be talking about little bit on the fallback events also, and little bit on the macronovas also. So what we know so far. So if we zoom this part, if we zoom this portion a little bit, then we will see this plot. So here we can see that there are different regions. This is basically the energetic range over which we used to see different kind of events. This is the regions where type 2Ps and type 2Ls are happening. These are the regions where type 1Bc is happening. These are the regions where a new kind of events known as superluminous supernovas, which just discovered first time in 2005. These are 10 to 100 times more luminous than canonical core collapse events. And these are happening. And there are some regions which is where we cannot say exactly whether it is a core collapse supernovas or superluminous supernovas. I just named it as an ILT. This is the interluminous transient strips, if you consider. Now, what we know that more or less that nowadays that these type 2Ps or type 2Ls, up to this much, we understand that these type 2Ps or type 2Ls are probably formed by is created by this massive stars like red supergiants, which has the hydrogen, and the end product is probably neutron stars. And I put a questions and I will discuss on this later. And there is a region where we used to see type 1b supernovas, where from the stars which do not have hydrogen, because these are much more massive, and due to wind, the outer hydrogen is stripped away mostly, and we don't see the hydrogen but the helium. This is the type 1b, and the more evolved star we used to see the type 1Cs even. But up to this was okay, but then if I go even beyond that, we used to see the events where we used to see both hydrogen as well as with or without hydrogen and helium, and we don't understand the regular supernovas explosions cannot explain actually this kind of explosion. This regular supernova theories cannot explain this kind of explosions. So there are new theories came up that this is probably the supernovas, but within a very dense shell, or instead of neutron star, probably there are magnetars. They are formed. And in this case also, we are not very much sure what is the final revenants. So these are the known and unknown things, the known and the issues, known issues, and there are few regions where we know that there is a mix-up of type 1, type 2s and type 1. For example, there are type 1b events and there are type 2 events. So in between, there are type 2b events are also, which initially show hydrogen, and then the hydrogen disappeared from the spectrum. So we know that this is the, very quickly I'm saying, this is the just before the supernovas which is happening, and this is the basically the collapse of the stars, and these information just comes in the form of gravitational wave or neutrinos, whereas in the other case, what we are actually, so in the other case, where it is, if we consider that it is a point explosions, then after that, these remnants, this ejecta which is going outward, this interacts with the circumstellar matter, and it's produce different kind of light curves in X-ray, UV, optical, and other kinds. So we basically talking about this part, and this is the time scale when we are getting the electromagnetic waves from this explosion. So this is very important, as Kuntal also mentioned, that how much early we can detect this kind of explosions in the optical. For example, here is an example. So this is an event which was actually an explosion in a yellow supergiant. But if these data points were not there, you could not differentiate it whether it is an explosion of an yellow supergiant or an ultra star. So there is a importance of the early data. So this presence of these two data actually makes the difference, and it says that this is actually explosion of an yellow supergiant rather than an ultra star. Similarly, we used to see we saw a long rise in superluminous supernovas just before these explosions. So these kind of things are actually related to the shock breakout phenomenon, which actually again maps what kind of events are happening here. So for this purpose, so early detections are very much important, and that's why the coordinations among different facilities are required. Moving ahead, so there are many surveys. I said it, this is the untargeted surveys, and these untargeted surveys are not observing a particular galaxies or nearby galaxies. Rather, they are observed randomly in the skies, and you can see that nowadays their reported transients are quite high in comparison to the conformation of the transients in the form of supernovas or any other transients. So there are different groups. Some used to discover and also characterize. So these are the groups who are involved in the discovery worldwide. There are groups which who are used to classification. For example, Pesto, NUTS. They are mainly involved in the classification. Some groups who does both detection and classifications. Some are the follow-ups. These are also important. So when it is detected and classified, it should be followed up. So there is a follow-up groups. They're doing follow-up, and there are some missions which are upcoming. So here is a typical statistics for an IPTF survey, which lasts for 3 years, and you can see within 3 years it could detect 910 core collapse supernovas. So this kind of untargeted survey actually detect many unknown kind of transient events, and for example, till last night, ZTF detected about 6,600 event, and it is classified. and 78 was tidal disruption, 231 were near Earth objects, and so on. And similarly, PESTO classified about 3,000 objects, and it is now following about thousands of them. So to improve the performance of different facilities, there are many new softwares and packages available. Tom Toolkit is one of them. It was developed by Las Cumbres Observatory. So its full is target and observation manager software. It has been used widely, mainly very well by the Gaia groups. So here is a tool. This is called the Black Hole Tom. It has been used for the microlensing event and its monitoring and with coordination. There is another necessity that to observe it simultaneously in different bands. So here is one example is the ESO ground, which can observe a particular event simultaneously in 5 bands in GRIZ. So this kind of facility, if we can develop for 1 meter plus telescope, we actually can save the time for many other programs. So UVBRI, if each band takes 5 minutes, so it will take half an hour. Instead of that, I mean, I'm saying roughly, there will be a plus minus thing. So it will be 5 to 10 minutes. So these kind of instruments are very much necessary for 1 meter plus telescope to take it in a more, to upgrade it. Next, certainly there are this kind of image subtraction techniques are required. People develop, for example, I developed it for one of the objects, and I later used for many cases. And for example, you can see that this kind of software, this kind of pipelines can detect the supernovas as faint as 22 Mach. So now I'm coming to what are the new things people are getting after doing this development. So first I'm saying about the flash spectroscopy. So flash spectroscopy is the spectroscopy of a flash. That means as soon as it is detected, if you take the spectrum, and if the detection is very early, we may actually may get some information about the atmosphere of the exploding star itself. For example, here is the star, which is an Wolf star. So this is the early spectrum taken about 15 hours after the actual burst, and this is the kind of black body spectrum, and then the spectrum evolved, and this is known as the flash spectrum, and we can study about the about the material of the atmosphere of the exploding star. You can see that this kind of spectrum can be taken from a 2 meter plus telescope. So it's quite possible to do. So this is one of the things. Second thing is people are also finding out the eruptions before the death. So this people find out because this is, for example, 40 days before the actual eruptions, the people find actual explosion, the eruption was observed. These are sort of imposters, and actually LBVs erupts just before the explosion. So these are the key areas people are now working, and when these eruptions happens, then with the early erupted material, supernova can actually interact, and it produces the lines. For example, here it is the type. This is the type 1C supernovas, which produce line after starting interacting with the surrounding shell. So these are the new things which people are now doing, and these are all being done with the 2 meter plus telescope. This can be done, and this photometry is of course from the 1 meter plus telescopes. Further, we found the peculiar events. So this is the type 2 events, normal type 2 events. which has very low, relatively low luminosity. So here is one event which showed a long plateau kind of things, and there is almost no change in the spectrum. So this is IPTF 14H, first time it was detected. And so far only 4 such events has been detected. And, and you can see none of the models can fit its light curve. So this black is not actually any model. It's just it just fit the data points. So, but we can see that they are actually locating in the more or less in a regular galaxies. So they are not. So we actually don't know what are the main mechanisms for this kind of exotic explosions. We also have seen that the superluminous supernovas and superluminous supernovas, here I am saying about a particular case of 2018 BSD, where we have seen that early rise, what I already said by Anderson, and then asymmetric in explosions, showing the through the spectropolarimetry. Brajesh will talk about more on the polarimetric part. Then first time we Pesto reported about the dust formation in the superluminous supernova. So these are the key areas which can be focused in the upcoming years from meter-class telescopes. And these are all observations are mainly from the meter-class telescopes. I will keep it just one slide on this fallback objects. So there are some events which where we found there is no supernova. So there was a star and suddenly it disappeared. So maybe it formed a black hole. There are kilonovas or macronovas. So there are different models of the macronovas and kilonovas. So these are the areas which are one of the key areas which can be focused in the future. But for this we need the HST observations mainly. So these are mainly done from the HST. Ground-based telescope is not capable to do this kind of things. Coming to the central part of the coming to the central part of the galaxies. So there are many new kind of transients. As I said, these are the tidal disruption events and nuclear supernovas, and people have found out many nuclear supernovas, and there are confusions also. The same objects once was detected, was classified as a superluminous supernova, later characterized as a tidal disruption events. So there are areas which should be explored, and in this TDs we know that T⁻⁵ is the theoretical power law decay, which sometimes followed by X-rays, but not always by optical, and we have seen in many cases, and it also shows spectral evolutions of the 3Ds. If you look dramatic changes in the spectral evolution, spectral lines. The Bowen fluorescence is one of the key lines which shows that the formation of accretion disk in the TDs. So these are the areas which can be done with the 1 to 2 meter plus telescope. This kind of observations can be done. And this is the last slide. So this is there are new objects that's coming up, which has been found in the center of the galaxies, which are neither TDs nor supernovas. For example, here one objects which actually happened at the center of a S0 galaxy, which is a dead galaxy. This is the SDSS spectrum, and you can see that it is just there is a sort of disk-like formation which makes the spectrum which give a transient-like phenomenon along with radio and X-ray emissions. So here we proposed a very simple model with a blazar-like structures without any torus or any BLR, anything. So it is just a simple disk which produces a blob, and you can actually fit the X-ray and radio with the same synchrotron emission. So, showing that the synchrotron emission is responsible for X-ray as well as the radio emissions, and whereas the optical and UV are actually coming from the disk part. So finally, just two things that just to mention that small class telescope can do many things. What we need a coordination. We need a coordinations among nationwise, among worldwide. So to get the proper thing at correct time. So that is the main thing I just want to say, and that's all.
Okay.
Maybe I took a little more time.
One quick question.
TDs need much faster response time, isn't it? So compared to say.
Not always. If you see in the optical, it takes a longer time. In comparison, I mean, sometimes it takes 30 days to rise time. But in nowadays, there are other dedicated satellites like TESS, which always observe the sky, can also get the rise of the TD very nicely. But actually, the fast transients, which I say the macronovas, they are actually very fast in comparison to others. They are rising time scale 1 to 1.5 Mach per day, which is much faster than others.
Because we did I asked this question, we did a discussion on following TDs with asteroseismic.
Yeah.
We came to the conclusion that decision cannot be made so.
Yeah. So, but yeah, because I know that.
Decision
Yeah.
rather than actually.
Yeah, so since I'm out of the field, probably the same question applies for Kuntal. So you are mentioning that the early phase is important. Now I want to know, detection is not enough. You need characterization also. So what is the typical time scales you characterize these events? Is it days? What is the current status?
So, for example,
is it days, weeks, or months?
it may be even hours.
Okay.
For example, I
to
showed you
have
one
it-
event.
hours
Hmm.
for many such events.
No,
You need
not-
an automatic data pipeline.
Yeah,
I'm just asking you what is the status of your virtual observatories and the automated data pipeline?
yeah.
Why do
individual-
you need, call to individuals and sponsors? Why the network is not providing the data into the public domain?
That's why the Tom toolkits are there. Tom toolkits, for example, Black Hole Tom is the particular is the platform where the Gaia, it is developed by Gaia, but has been but they have used the Tom toolkit.
Yeah, but the
But
top
they
toolkit
say-
will only work with the data if it is available locally.
Hmm.
Unless your data is available globally, you cannot apply the data, na?
No, but they actually inform to
That's again, while you inform and then the data is available for the, particular pipeline to work on, data availability is required. So is virtual observatory providing you data? I mean, are people putting the data in the virtual observatory?
not all data. CTF public is there, so that they provide the
No,
data.
I will
Atlas-
break this discussion
Atlas
in the
pro-
last part.
Atlas
So if you are
provided-
talking about survey telescope, if you are talking about better discovery and better science, you have to ensure the facilities are also uploading the data into the virtual observatory or whatever platform you have.
Yeah.
On the real time, not on after, call and, emails and so on.
And you can also prepare it just for
Photometric.
analyzing.
Yeah.
So this is your generation was.
Spectroscope.
IMT data has to be there available
Yes, sir.
to the
Actually,
global repository.
this is what our plan is. As ma'am told me, like we are preparing to make the data available immediately.
So that is one element. The other element is I was wondering, you need to also, if you were to trace back the early phase, suppose you detect something, you still have an early phase, we have to go minus, right? Negative time frame.
And that's an idea.
So that is also
Because
very much
those
important.
will serve as templates for the subtraction. Because any image subtraction algorithm will only work when we have the templates. So during the commissioning phase or over the next 6 months, whatever strip of sky has been observed, those will be saved as templates for future.
So that's AIML. That is what AIML is required.
But one more problem I think is that there is a problem of plenty. Like we'll have too many.
Of course, so you have to just attack one at a time, but you identify the challenges and then you address it.
Now,
Very useful because for a robust classification, spectroscopy is
Is
necessary.
required.
spectroscopy
He also said about
I agree,
ZTF.
I agree.
ZTF is only the magnitude.
magnitudes, and the problem is ZTF is not giving it to all.
I don't even specifying, I know characterization needs a spectroscopy.
And ZTF is not giving to all. In every 3 days, they used to make it public.
No, when that too, only
Understand?
a certain data they make public. If they find something interesting, they don't make it public.
That is the problem.
Okay,
Okay.
okay, let us, we can continue this one. So the last.
That's why, I mean, within national level, probably. we
Rajesh?
should also think about it.
You're meeting 2 weeks, man.
Huh?
You mentioned ASI, you're meeting in 2 weeks, you're
Oh.
there.
The polarization properties of supernova.
National level.
Forward, backward.
Huge, but-
Future.
Yeah, but you should start.
No, what I meant was during this expert meeting, these all should.
We will have a vote.
So, good morning, everyone. So, I will be presenting about polarization property of supernovae, and mainly what is the important role of Sampurnanand telescope, which has I mean we have used it very intensively, and I will be presenting this work on behalf of Aries Supernova Group. So mainly 3 topics I am going to cover here: some basic concepts about supernova polarimetry, and what main studies we have done since last almost 10 years, and then summarize my work. So I would just like to share with you that along with ILMT, I have been also working in transients. So we, as Kuntal and previous speakers said, that what are the major importance of light curve by spectroscopy. But we started this project during my PhD in 2012. There was one very bright supernova, 2012 AW, that was type 2 of the event. And after that, you can see that it was possible to observe several supernovae and publish our work in very, good journals. So already the previous speakers already said about the imaging and how we can estimate various equivalent parameters with the light curve, and using a spectrum we can understand the composition and line velocity evolution, and mainly with polarization we can investigate the asymmetric property of the explosion. And mainly for the polarimetry we use imaging polarimetry and spectropolarimetry. And what are the benefits of this different kind of observing plans? So for the spectropolarimetry, it infers the geometrical and dynamic information for the different chemical constituents of the supernova explosion. But this technique is photon hungry, and so it needs larger big facilities. And this is good for brighter events. However, imaging polarimetry is good, and like 1 meter class telescope, these are good facilities. We can monitor it even for fainter objects and for a longer time. So for longer coverage and multi-epoch observations, it's very useful for 1 meter class facility. However, multi-epoch polarimetric data of supernovae are limited. It's around 3 dozen of supernovae in the date. So considering this, since last few years, we have started monitoring different kind of supernovae using Sampurnanand telescope mainly. So the first supernova which has been observed was supernova 1987A in a large magnetic cloud, and the first multi-epoch polarization of this supernova was done by Joshi et al. And Jeffrey 1991. And here you can see that the maximum polarization was around 1 degree, 1%. And a dust shell model was proposed to explain the polarization property of supernova 87A. Here I would just like to emphasize that there are two main phases of supernova evolution. So the first one is the photospheric phase. This one. So in this case, we in this phase, if we can properly investigate, then we can understand the ejecta property. However, in nebular phase, as we can go deeper, so we can understand the property of core. So both photospheric phase and nebular phase monitoring in both phases are very important. This I'm just skipping because you have already seen in previous presentations. Here how we can understand about the polarization property of supernovae. So since supernova ejecta is very hot, so electron scattering causes the supernova polarization. So if it is spherical explosion, then the polarization vectors cancel each other and the net polarization will be 0. However, if there is asphericity or clumpy ejecta, then it will be not cancelled out and we can get a net polarization. I will tell about interstellar polarization because the supernova polarization may vary. However, it may be possible that it is not intrinsic. So we have to remove the interstellar polarization from the observed polarization values. Usually, the galactic dust follow mean polarization efficiency relation, and also in some cases maximum polarization efficiency. That is, P mean is 5 times EP minus P, or P max is 9 into EP minus P. Type 1A supernovae and core polar supernovae. I'm not explaining very much, but in case of type 1A supernovae, the degree of polarization is have been found around 0.5%, and it is generally it has been found that globally these are spherical explosions. However, in case of core polar supernovae, the polarization degree has been found very much around 5%, and it may vary during the evolution phases. Here you can see that this is one very good example that during the photospheric phase, the polarization was very less, around 0. However, as the core revealed, the polarization increased very much, and then it evolved, it decreases. So we started polarimetric observations. First supernova was 2012 AW. This was type 2P event, and we took 9 epoch R-band observation with M-pole up to 90 days. And we constrained the interstellar polarization using several field stars. Here is the plot. And we used a mean polarization efficiency relation, and we also used considering that the host galaxy is following the mean polarization efficiency. So we also used this relation and estimated the host galaxy polarization as well, and then subtracted it from the observed values. Here is the plot. This is light curve of this event, and these are the observed and intrinsic polarization plotted here. And you can see that it's following the polarization is following the light curve, in fact. it's possible that the changes arise due to the possible presence of clumps in the ejecta. Here we have compared different kind of, different type 2 events. And the main thing is here that if you see carefully, so here in the initial phase, this event is following supernova 1987A. This is another event. This is a transitional event between linear. So we use aim-pole instrument and observe it at 6 epochs, and mainly these observations were in the nebular phases. So to estimate the interstellar polarization, we used different approaches, and finally we considered this value as a interstellar polarization, and then we subtracted this. However, you can see that this is the plot of polarization values, and these are the plots for these stars, which are we considered it as a field stars. So you can see that here there is almost no variation. However, in this case, left panel, there is variation. Although the error bars are very much, however, we consider that since we estimated the interstellar polarization in a very robust way, so we consider that these are intrinsic values. And in this slide, I am showing that we have compared with similar type of events. Just see here. In this case, supernova 2004 DJ, in similar phase, the nebular phases, it was around zero polarization, then it suddenly increased, then decreased. However, here there is a different trend. So it also indicates that there is diversity in the degree of symmetricity. Then in another study, we investigated a type 2n event, which was at around 73 megaparsec. It was a very bright event, minus around 21 magnitude. And for this study, we used aim-pole and also swift observations, and one spectrum was taken with SCT, and two observation was taken with 1.5 meter Canada telescope. So we used a similar procedure as I discussed previously, and we estimated the interstellar polarization, and this is a light curve. Using the swift data, and this is the spectrum compared with similar type of events here. So as you can see, this is another very bright event. So in this case, the supernova 2017 SCC spectrum is comparatively bluer, and also the hydrogen line emission lines are evident in all events, but rather in 2012 AB and 2010 JL. However, in case of 17 SCC, sodium only lines are negligible. So we consider that probably there is less reddening toward the supernova site. And we estimated physical properties of supernova, this event, and this is parameters estimated from black body fit, and we also try to estimate the mass loss rate using this relation, and the estimated mass loss was around 0.12 solar mass per year, which is a typical mass loss rate of luminous blue variable. So we considered that the progenitor of this event was a luminous blue variable star. We again compared it with polarization property of similar events, and here you can see that this is the most polarized event till the date, of this kind of supernova. Then in one recent study, we have studied another event, type 1b event, and recently it has been published. Here we consider that we suggest that if you see here, there are variations in polarization parameters, and it represents that the explosion was aspherical, and or possibly also it may be possible that there were a clumpy ejecta in the explosion. These are some other studies and similar type 2 events, and in the left panel, this is sorry. So this is showing the supernova 13Hj, and another, this one is supernova 14G. In one case, you can see there is variation of polarization, and but in another case, 14G, there is no significant polarization. However, in the right panel, it seems that there is up to this level there is almost the polarization level is almost around 0.5, but it seems that there is a variation. So this is the summary of my presentation. So here I would like to emphasize that using 1 meter class telescope, we can use this facility and try to understand this kind of events, which can be very useful to investigate the symmetric property of supernovae. So, thank you.
Okay, Archana.
Thank you. Do you have multi-band observations of these multi-band polarimetric observations of these supernova?
Actually, one object was observed multi-band, but since, as you know, that I would, along with that, I would like to acknowledge that at that time, we started it as a pilot project.
No.
And sorry, let me. Okay.
This is something I want to do here, because you started with the interstellar polarization, and you are somewhere citing the Sampurnanand thing. Because if you have multiple polarization for all these supernovae, you can do the Sampurnanand for these things and compare the lambda max what we have in our galaxy with these extra galaxies. Then you can very easily compare that what is the dust distribution in our galaxy, in ISM and in the other ISM of the galaxies. That's a very important thing we have to do to understand the dust distribution and the size distribution specifically actually in all over actually around us. So multiple polarization observations are very important in these subjects.
Yeah, you are correct. I understand your point.
Most of the time, the supernovas were being from here, so around 16 times, 17 times, 18 times. So if you talk about the multi-band polarization, I think blue band, those bands.
No. We can start with B. I know you is the one who is really needed. We need to see that. But we can start with the B, like BBRI. That is important because the other ISM is also
One band and other band.
so at least 2-3 bands are important.
In B band, how much significant is it depends on the polarization that I have? No, I'm not talking about the polarization. Okay.
No,
So I think it's a good idea. Only thing, if you have data, make use of them.
yes.
I think that's the message I get.
Single band observation are not going to give us.
No,
more information
I
other than
fully
the
understand your point. The problem was, as you know, that we started it, just as a pilot project. Yes. Yes. But I am thankful to you as well. Since whenever there was some time, I think that I did not support you, but whenever there was some time, I was trying to utilize that at that time.
For all these transients, ask a polarimeter also.
Right. So I hope that the
You will be there.
upcoming spectropolarimetry.
Okay, Deepak.
Okay, so again, I'm out of the field, so it's easier for me to be critical. see, you talk about clumps, so to me, these are all conjectures and all. How far the simulations, match? What is the status of the numerical simulation in these scenarios? You are talking about different scenarios. I mean, I guess they're possible to be simulated. So what is the status? I didn't see any of your simulation, anybody showing that.
Actually, simulations are there. I mean, we are not performing simulations.
You don't have to perform the
Yeah,
simulation.
but other can perform it. Yes.
Compare with the
Yes.
simulation
Yes.
result.
I think if I'm not wrong, also not working in the field at least for more than a decade. You see, somewhere you estimated mass range. That will come definitely if you are modeling and.
Yeah.
Yes.
Yeah. So what is the
So you are
motivation?
used.
Yes.
I think that's what he wanted.
Yeah. So what are the, because you don't have to conjecture.
Yes.
This, see, I mean, clumps will be some stuff, some form of instabilities, right?
Yes.
And you are talking about some polarizations. Obviously, there will be magnetic field also involved. So there will be some status update from the simulation results.
And these are not like the fixed locations of the clumps, they move, so your polarization.
Obviously.
get a
So,
lot
yeah,
of-
so that is the reason why we need, follow kind of
No, but are there, current simulation available?
simulations.
Just one, I mean, this simulation of what? I mean, of supernova?
Simulation of the, yeah, supernova, the environment.
The super-
dynamic,
The
behavior.
simulations are there.
Why you are not showing that?
The thing is, in fact, making a spherical supernova is difficult. So when due to its neutrino, I mean, if you talk to us of
I actually hear what he's trying to convey. Basically, while you are doing modeling, you cannot reproduce the physical conditions because here.
I was surprised because the physics and the computational domain has,
I think.
enormously progressed. Why? I mean, I'm not in the field. I would be surprised that it is not there. Yeah.
Because Turkicity and evolution, basically, what you are trying to understand is stellar evolution, how it is going to, because mass was way,
Yes.
progenitor
Of
mass.
course, the time dynamics would be, quite bit challenging,
It will,
but you can have quasi, static models that must be
There
there.
are several hydrodynamic
I think.
Yeah, there have to be. I mean, I
And
can't.
then the use of those hydrodynamic simulations to generate the synthetic light curves.
Right.
Take all the different mass of the progenitor star and explode the stars,
Yeah.
and then different species could be present, and also by the asymmetry, these asymmetries could be seen in the form of different spectral features that we see. And modeling those spectral features, we are able to identify what degree of asphericity is present in those explosions, and also the nature of the clumpy ejecta. In fact, we've done that.
even because I have been saying that these people are using this simulation.
So why I'm provoking this discussion is, it is now time to work with them also. Collaborations with the modelers and all that will actually pinpoint the physical process also.
Some made them public.
We should use them. I should use them.
Yeah, so I think some
No, no.
people are already using some students, I think in the.
Now,
So those models are mainly for spectral modeling. So I mean,
Yes.
some elements.
But time modeling was also there, I think light curve modeling was there.
No, light curve models are also there.
Okay, we can discuss based on that.
Okay, yeah.
Okay.
Sir.
Depending how the speakers have discussion. And then there's some announcement by Viren.
Yeah, so the photo booklets have arrived. I request all of you to collect your copies just outside during the tea break. And I would request Aries members to give preference to non-Aries participants first to collect their copy.
And the tea break. Okay, 11:30. Let's simply start at 11:30.
So 11.
Yeah.
Not 11:1.
What is the time? 11:20, right?
11:30, please start.
Observation से बोलेंगे ना, definitely बोलेंगे
But at the same time, things cannot come.
the same person may not be able to. What the heck?
You have to have a group,
Yeah, तो मैं वही बोल रहा हूँ कि आप collaborate करो ना.
collaborate. In the
आप
best.
collaborate कर ले, observer के साथ theoretician से भी करो.
नहीं, at least in Dipankar Bhattacharya,
Yeah.
he always tell, I'm not observing. And he knows, not so. It's a very. No, not only that. Other thing I will tell you very important. So, you see, observation, whatever based in Nainital, he proposed a model to explain. We have variety, P key values or whatever you have converted. Then we came up with a new thing. We all published in bulletin because that was our decision that all these things will be published. And that paper had more than 60 or 70 citations. Theoretical paper based on this. So it is there, only thing. Narsimha, for example, micrology. So these efforts were made. And I know. नहीं लेकिन वो अच्छा है और उसको आगे बढ़ाना है नहीं I will be there.
कोई बात नहीं
वो तो वो आस्था का प्रश्न है
उसके बाद है
नहीं वो I have noted it. After lunch I will.
ठीक है
बस लंच के और इन लोगों के
Now I am going to the site and this is
I saw that so that
now
working. Well, so based that I will be there.
I may not participate in that.
Yeah, so I think Rajesh, you coordinated the site. I also will not come because the dot.
I will be like it there.
Yeah, the director will be there.
नहीं अभी कुछ नहीं मैं हफ्ते में जाता हूँ सर मैं थ्योरी करता हूँ ये मैं
भी करता हूँ
नहीं अनुपम भी बोल रहा है कि better late than never so now you're asking a lot of night sky questions so finally you're becoming a night
makes a difference of course. शेड्यूल क्या हो
वो पता कर लेंगे 9:30 से पहले यहाँ पे तो एक्चुअली वहाँ पे आप कोई जगह ये करना पड़ेगा ऊपर में मेरा एक मॉर्निंग मीटिंग है
लाइव क्लास नहीं करनी है लीडर बनाना है
अब करते रहिए बिकॉज़ इधर ही वो दूसरा कोई ना कोई हमारे तरफ से होगा बिकॉज़ ज्यादा
नहीं उस टाइम में निकालूंगा नो प्रॉब्लम
नहीं बिकॉज़ गार्ड का स्टेप ना अभी भी रेडी नहीं होगा तो कुछ नहीं करना मराठी को उतने प्रोवाइड करना what about these
Good combination, I mean, good distribution.
The problem is that the algorithm doesn't work very well for want to ask me something anytime. It doesn't work very well for probabilities. It works well for, let's say we are subtracting two globulars. And we can
Actually, the problem of very sophisticated instruments.
मैडम बताइए
So that's why मेरा होगा एडी स्टॉक एडी स्टॉक ऊपर चलिए एडीज नाम से फोल्डर बस एडीज से नाम से फोल्डर नहीं एडी स्टॉक नहीं ये ना ना इसमें मैं लाई हूँ ना एडी स्टॉक इज नॉट इजी I mean, one page,
Something they told me. Something they told. I put one slide there.
Sir, can you test the mic for me? Actually, I've been some changes with anyway, you can first I will with the right? Yes. And it connects to X-rays. But here, yes, sir. There is a top. No, the gaussian beam is connecting to X-ray. Yes, otherwise it will go like.
Hello.
Okay, X-rays are here.
Hello.
You are not connecting X-ray. You are connecting optical and.
Hello.
They are showing that what they show you, that the X-rays do not fall on the
Hello.
continuation of.
Hello.
Okay, in both cases.
Clear, huh? Clear.
Just again. Clear. So master volume was.
Hello. Hello.
Part of the same.
Hello. Clear, huh? Noisy.
Now it is.
Okay.
Can you roam nearby the podium because that's the part where
Hello.
distortion started.
Hello. Hello. Clear, huh?
Just I have to give you the base.
Hello. Hello. Hello.
Starting your is the first topic.
Mine is the step.
The last.
Hello. No. Hello. Clear. Clear, huh? Clear, huh? Load them.
Javed मुझसे or somebody had left mobile there.
Yeah, मेरा है.
Manas has left somewhere and he could not get back. तो उसको जेब में रखो. Yes, now इससे कुछ frequency का match हो सकता है. तो then
नहीं अब नहीं होगा.
अभी नहीं होगा ना. नहीं तो आपका उसको
अभी एक तीसरा
हाँ तब कोई
नहीं वो दिमाग में कुछ अलग आया तो कुछ बनाया है ये तो अभी सारा ऑडियो कंट्रोल आपका यहाँ से नहीं सुनाई देगा. हेलो 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 हेलो
ये चीजें देख के फिर समझ में आता है कि ने चाय लीजिए।
हाँ मैंने लिया फर्स्ट जनवरी से इधर ही क्या ठीक है हाँ करेक्ट
Yes, no, I just switch it off.
आप कर
नहीं अभी ऑफ कर दीजिए तो टॉप होगा then you can start. 3
They are saying it on the basis of polarization. They are saying that the mechanical is reducing on radiation. For the selling company, yes, as well. Because X-ray they can measure polarization, but since X-ray can see UV, they interpret the selling component and there's both UV and X-ray. Actually, I was also thinking that they have said like there are like skill debate on what have produced the X-ray here. So whether it is come from US content or I'm not taking it. Actually, there was some if we taking in this organization of micro CMA photons, then what happened like beaming effect will cause a scattering of photons in every direction. Like they were in US content, actually I was not getting that. It's almost like saying that okay. So if they they will scatter in all directions. The comes from the collide with the there is no radiation to provide because of many very standard signature of single tone. The mega polarization some details polarization then you can see भेजा नहीं भेजा तो 3 बार मुझे ईमेल
ये वाला चल रहा है?
हाँ ये भी चल रहा है।
यहीं पर ज्यादा
ये
time-
पाँव नीचे रख ध्यान दीजिएगा।
Okay, we shall start now. So please. So good morning, everyone. So welcome to the session on galaxies and active galaxies. So as you know that apart from several other fields that we have already discussed, ST has significantly contributed to the study of galaxies and AGN. So we'll hear some of the talks about that. And there will be 4 talks in the session. The first one, I would invite Professor C.S. Stalin to talk about quasar variability studies at the 104 centimeter telescope, a modest start to high impact science. So Stalin, the floor is yours. I will remind you 5 minutes.
Okay. Thanks. So I thank the organizers for the invitation for this meeting. And it is a good feeling to be here, being part of the 50-year celebration of the Sampurnanand telescope here. And I really feel happy to be here because this is the place where my research career took the birth here. So 25 years ago. And I use this occasion to thank my supervisors, Professor Ramsagar and Professor Gopalakrishna, who are here, who introduced me to work on AGN variability using data completely from the 100% telescope. Okay, so completely from the completely from the 100% telescope. And I also would like to find out the place where Aries is right now is only because of the dedication and hard work that was done some 23 years before in late 1990s and early 2000. And I wish Aries much more success in the coming years. And with these words, I just move on to my talk, which I have titled as Quasar Studies with the 104 telescope, a modest start to high impact science. So yeah, to start with, so you all know that quasars were discovered about 6 decades ago, and in 1963 by Schmidt. Soon after the discovery, it was realized that these sources show flux variations, and firstly, it was detected in the source 3C48, where people reported a change of around 4% in 15 minutes of time. And subsequent to this, people have observed variations in many sources, but all these claims of variability were taken with skepticism till the coming up of CCDs in the year 1980s. And the first detection of variability on short time scales of 15 minutes was recorded in using CCDs was reported in Nature article in 1989. And since then, many reports were available on the variations in the optical band. In addition to optical band, variations were also reported in other bands of the electromagnetic spectrum. Now, CCDs were coming up, many reports of variability were being studied from other instruments across the globe, and in India, the modest start of variability studies happened in the Meinel Observatory. And this was done by Professor Ramsagar and Professor Gopalakrishna when the VBT was getting commissioned. So they did some observations using the VBT, and what I show here is the first paper which came out of the VBT observations. It was in 1993, and this effort, the initial effort, they could not find any convincing evidence of variability. However, they continued the observations using the VBT, and here the next paper came in 1995, where they studied a radio moderate quasar and 6 radio quake quasars. And this was the paper where they reported conclusive evidence of variability in a radio quake quasar. It was published in 1995. And what is shown here on the top 2 panels is the differential light curve between 2 comparison stars. So as you can see, they are non-variable. And the bottom 3 panels show the differential light curves of the quasar with respect to the comparison stars. And the use of CCDs as in-charge photometry, photometer is an advantageous one because you take care of all the instrumental effects coming there, whether it's from instrument or from atmosphere. All these things are taken care of. So this is a very efficient method to look for very minor variations. However, the observations from VBT, what they attempted, they were not able to detect very small variations. They were able to go up to 3 or 4% level only because of various other factors. So the conclusive evidence of variations came here because they found correlated variations both in amplitude and time. So this is how it is established that variations were known in this radio quake quasar. This was a story in 1995. And then there was a transition of these studies from VBT to UPSO. So that was a time when Professor Ramsagar also moved to Nainital, to UPSO. And between 1993 and 1997, many groups around the globe, they started to do similar work. So here I have pointed few groups, 4 groups. And all these people have different sample selection, different methods of observation, different methods of work, analysis. So all these groups came up with different conclusions. Some say there is no difference, some say there is difference. This is highly confusing. So the summary of all these observation programs is that irrespective of the above tentative conclusion of the detection of variation from VBT, the scenario in 1990s were completely confusing. So this demanded that there's a requirement of systematic characterization of the intranet variability of the high luminosity agent classes. So this was the requirement at that time. And this was the drive for the initiation of this program in UPSO. And that was the time I was also starting my PhD. So I was also trying to look into some observational studies on AGN. After spending a couple of years on solar spectroscopy, and I was doing some surface photometry of galaxies, Dr. B. Visanan also, who is also here. So I observed a few galaxies also for surface photometry. Then subsequently, I was trying to look for studies on AGN. Those days during our PhD career, we were taken cold start by faculties from outside the institute. So Professor Gopalakrishna was visiting NCRA and visiting UPSO, and he was teaching us extragalactic astrophysics. So I was asked by Professor Ramsagar to go and meet him. So I met him. I told whatever ideas I had at that time. So he told these ideas are not possible using 1.1 meter telescope. It was completely shut down, and he told, why don't you come to NCRA? So that was my visit to NCRA, and in NCRA I spent some 2 weeks there, and that is the time we came up with this program of a systematic investigation of AGN variability using UPSO. So what I did, I spent 2 weeks in NCRA, and the important task, the base of the whole program rested in arriving at a uniform and complete sample of sources. So what we did, we went through a catalog of AGN. We selected 7 sets of bright AGN, putting a cutoff of 16 magnitude in the B band. This cutoff was necessary because we want to get good signal to noise ratio observations in the integration time of around 5 to 10 minutes. So that was the requirement. And we selected 7 sets of sources, and each set occupies a small redshift bin, and they span the redshift from 0.17 to 2.2. And in each redshift bin, we also carefully selected one radioquake quasar, a BL-like object, a core-dominated quasar, and a lobe-dominated quasar. Therefore, each set has 4 sources, and these sources are also selected carefully such that they match in the redshift and absolute brightness spectrum. And when we talk of radio quiet quasar, we selected quasars that are purely radio quiet using a cutoff from the radio brightness parameter R. We selected this R parameter to be less than 1 because this R is nothing but the ratio of the flux density in the radio at 5 GHz to the optical flux density 4,400 angstrom. So this is the criteria we adopted. And the other stringent condition what we did was we demanded that each agent has to be monitored for 4 to 8 hours continuously, and each source must have at least 3 nights of observation. This was the condition. And we selected exposure time typically of 300 to 600 seconds. And to complete this program, we took some 113 nights, which amounted to 720 hours of observation. But an equal number of nights also got wasted because the demand was to have minimum 4 hours of continuous observation. So in many cases, we have 1 hour, then there's a break of 2 hours, then another 1 hour. So these observations all got wasted. But however, we published those observations separately as apart from this project. So this is what result we got as part of this program. And I would stress that this kind of data we were able to accumulate only because of the careful observation, planning, and tied up with a careful analysis. So these coupled together, we were able to find variations of the order of 0.01 magnitude. Yes. So what is shown here in the top panel is the differential light curve of the quasar with respect to comparison stars, and these are the differential light curves of between comparison star themselves. The point to be noted here is the whole range is 0.03 magnitude. So the typical error in the differential light curve of a non-variable star is of the order of 0.005. So because of this careful analysis, we are able to detect variation of the order of 0.01 magnitude in this source. And this study led to the first clear evidence of intra-night variability in radio quiet quasar, which also leads us to conclude that radio quiet quasars also have relativistic jets. The conclusion we are drawing based on the following thing, because prior to this study, people thought there are 2 competing theories. Variability can be because of accretion disk, and it can be also because of jets. So our idea to thought is we have radio quiet quasar and we have radio load quasar. We know radio load have jets. So if it is because of jets, then the variation seen from these 2 populations must be different. Alternatively, it is because of accretion disk. They both must show similar variability. That was the thought that time. So when you look into the amplitude of variability, we found both radio quiet quasars and BLX show similar variations if you restrict our amplitude of variability to be less than 3%, roughly 0.03 magnitude. However, if you restrict sources to be having amplitude more than 3%, BLX are definitely more variable than radio quiet quasars. So the conclusion what we draw from the above project is that the low variation which we see in radio quiet quasars may be because of the observers marginally misaligned from the jet direction, so that they will observe a drastically reduced intra-night variability. The thing is, the same object can appear to be highly variable if it is slightly misaligned with the observer. So what we show here, because as you see, if you have a jet, it is having Doppler boosted. So this has 2 effects. It can amplify the flux and it can shorten the time scale. So here we took a typical observing run of what? 8 hours, a Doppler factor of 8.1. We slightly change the Doppler factor gradually. And the same 8-hour run is maintained here. This is each interval is 8 hours. The same object having delta 8.1 appears to be highly variable.
This is simulated part.
Yes. So it's the same, but from the observed data. This is the observed light curve. From the observed light curve, we try to change the delta so that flux also changes, the time scale also gets stretched. So now if you see the same object which appears to be variable, if it is a lower delta, in the 8 hours of monitoring which we are monitoring, the source will become a non-variable. So this is the inference, and what we concluded, radio quake quasars also have optical synchrotron jets as active as the jets of blazars. And the dichotomy what we know between radio loud and radio quake quasars do not imply a fundamental difference in the central impulse. This is the conclusion of that study. And now I will move on from UPSO to Aries era. So the same technique what we adopted in 2002, this was carried on to Aries, where people from Aries try to concentrate on more different types of aging. So, for example, they try to work on characterizing the intranet variability of radio intermediate quasars. They also try to understand what is the role of optical polarization in the intranet variability observed. They also try to characterize the intranet variability of different classes, such as radio quake quasar, radio intermediate quasars, lobe dominated. So all these kinds of studies were going on in the Aries era. And these studies led to some conclusion of a physical link of intranet optical variability with optical polarization. And they say this polarization is much more fundamental than the beaming of relative jets in Asia. So this is the things which happened in the Aries era. So this is the conclusion which came up from that era. So these kind of studies are further followed up. So here they carried out an extension to the what things were done in 2000. They tried to characterize the variability of low mass AGN. So low mass AGN is typically, we know AGN are powered by supermassive black holes of 10^6 to 10^9 solar masses, but however now many surveys have come up with the intermediate mass black holes powering AGN, having mass of the order of 10^4 to 10^5 solar masses. So here they try to characterize the INOV of 10^6 solar mass black sources. So here the finding is that even in low black hole mass powered systems, they were able to find blazar kind of activity in the system. So this is the conclusion which came just as a recent work in 2022. And they in Aries they also extended this to different classes of AGN. So here is the result which came out on PV emitting blazars. So this is also in the Aries era. Then this, not from the Sampurnanand, but it's from the 1.3 meter telescope, because this was in the time of around 2008, 2010. Fermi came up with the detection of gamma ray emission in 4 northern separate galaxies. Because prior to this discovery, people thought these northern seafoods are hosted by spirals, so they cannot launch jets, whereas blazars are hosted by ellipticals and they can launch jets. This is the famous elliptical jet paradigm. But when Fermi detected gamma ray emission, it gives a clear indication that these sources have relativistic jets. It's very clear. So what we did, we want to see if since these sources have relativistic jets, then the intranet properties must be similar to blazar. That's what the idea we want to test. That was the time I came to Devastal for the 1.3 meter inauguration. I was called, so I visited Devastal. So after this inauguration, there was some time available for some observations. So that was the time when Fermi was this report came. So what we did during that time, we tried to monitor some. There are only 4 sources, and one was in the southern hemisphere, which we could not observe. So we monitored all the 4 sources, and these are the results of that work. So here, what is shown, the top panel is the differential light curve of 2 comparison stars, and the next 2 panels are the differential light curve of the Narland seafloor with respect to the comparison star, and the bottom panel is what? The variation in the equilibration. So the conclusion what we arrived at this work is Narland seafloors, which are detected in the gamma rays, they have similar variability characteristics as blazars, and therefore whatever INO we see in them is because of relativistic jets. And I would like to point out this was the first science paper which came from the 1.3 meter telescope. So these are other. So we continued this monitoring back in using the 1.3 meter in Kavlur also. So these are the results from the gamma ray emitting blazars. So that was for gamma ray emitting Narland seafloors. So we continued we selected a sample of gamma ray emitting blazars and tried to look into the properties. And the conclusion we draw from this study is that the high intranet optical variability is associated with the high gamma ray state. So whenever a source is having the high gamma ray activity, that is also showing high intranet optical variability. And this is already noted by the noted with the results from the Aries or UPSO. High INOV is also associated with high optical pole density. So these are some other results from the 1.3 meter JCBT. And again, using 1.3 meter in Devastal as well as the 2 meter in HCT, we try to do a comparative analysis. What we did, we know 4 gamma ray emitting sources. We want to see how their variability compare with gamma ray non-emitting sources as well as radio quake quasars. So we have 4 sources. We took a comparison sample of 4 gamma ray loud sources, 4 gamma ray quake sources, but they are gamma ray quake, but they are radio loud, and 4 radio quake sources. We did a systematic analysis, and the conclusion what we draw is the gamma ray loud sources have high duty cycle and high amplitude variability, whereas radio quake quasars do not show such variations. However, though there is a similarity, there are lots of ambiguities. Still, we do not know what are the host galaxies of these sources, whether they are spirals or whether they are ellipticals. This is not solved yet. And we also have an ambiguity on the black hole mass of the system, whether they are powered by low mass black holes or whether they are powered by high mass black holes. Irrespective of these two ambiguities, the result which came out clearly is that gamma ray emitting asteroids are really more variable than the other categories of sources. So I'll just summarize this. In the invitation, they also asked me to tell something what we can do on 1 meter class facilities. So there was some mentioning there. So I'll just summarize here and move on to what we can do using 1 meter facilities. So I'll summarize what all variability we know on AGN. The journey started in 1990s from VBT. So from VBT, the whole focus moved to the UPSO in 1998. And from UPSO, it moved to Aries. And post this kind of program is being run by many institutes. So it is being followed up in IEA, because from here I got a job in IEA. So I was doing the same thing in IEA also. It migrated from here to Bangalore. Then it also, in PR also people started doing these things. Then now when Khumchand moved to Himachal, okay, he is also doing, and it got it. People in Manipal are doing, and people from Presidency University also started doing this. So the summary of this journey which started in 1990s is that though we are able to characterize the variability, it has spread to many institutes in the country. And this initial program which started as produced few hundreds of refereed publications, and there are few thousands of citations, because about a couple of years ago when I checked the citation, it crossed more than 2,500, because I want to get the number, but it's taking too much time, so I could not get the accurate number, and it has resulted in few theses. So this is the journey so far.
Tens of theses, I would say.
Yeah, few tens of theses. So this is the journey so far, what has started in 1998 in UPSO. But now we have to because now, okay, someone is studying radio quake quasar, someone is studying radio intermediate quasar, someone is doing Nerland secret. So only the objects are changing. So what can we do next year? Do you want to think beyond that? That's the question we want to ask. So I'll just focus one area which needs some thought is on the polarization in quasars. So what do we know till now? So here I show some slide where the top panel is the gamma ray variation from the Fermi Gamma Ray Telescope. The second panel is the optical variability. Third panel is the polarization, and fourth is the position angle. So what we notice here, there is a clear association between the optical flux variability and the polarization degree. Though this is clear in this figure, the situation is very more complicated, which can be seen in this figure. So we found instances, because we attacked a sample of BLX and flash pattern quasar. The situation is so complicated. We found instances where there are correlation. We found instances when there is an anti-correlation, and we also found cases where there is no correlation at all. So the relation between polarization and optical flux is highly complex. This is the summary. So I just show a blow-up version. Optical flux is going up, polarization is coming down. Here you can case optical is also going up, polarization is also going. So it's a one-to-one correspondent. So what we did, the summary from this study is the correlation between optical and polarization is highly complex. We have anti-correlation, we have correlation, and we have random variation also. And this kind of pattern is same for flash pattern quasars and BLX. So what I show here is for the long time scales. We also investigated this on the short time scales with Sondu. So this was based on the polarization from the 1 meter in Kavlu. And the flux monitoring was carried out in the 13. We have a small 13 telescope also. There we did this because two people stayed in Kavlu. Suvandu also stayed in Kavlu, Vaidhi also stayed. Had these two people not stayed in Kavlu, this could not have happened. So somebody has to be stationed in the telescope. Only in such cases, this kind of observation will be possible. Otherwise, it's highly impossible. So the same pattern is seen on the short time scale also. So the thought, this is just our personal thoughts. So what one needs to have a dedicated polarization monitoring program to pinpoint the complex interplay between flux and polarization variation. So this is one thought which we can think of in the future. The second thought which I put is on multi-band, simultaneous multi-band image. So one of the problems in quasar variability studies is how the spectrum changes the flux. Because people say there's a harder and brighter trend because the spectrum hardens when the flux is brightening, and there's another thought where the spectrum softens when it's brighter. So there's no universal behavior in these sources, and the only way to tackle is to have a simultaneous imager. The idea proposed could be one could think of a three-channel imager, or one can even think of a 7-band imager similar to the ground concept. The ground has a 7-band simultaneous imager. So if you have such a system on a small telescope like 1 meter, we will be able to try to pinpoint what is the spectral nature of these sources. So this is a second thought which can be thought for small telescopes. So till now we have thought about using variability as a tool to understand the physics of region. Now I will flash 2 slides where we will use the variability as a tool to find some of the properties of the sources. First is to weigh black holes, how to measure the mass. So here I show an example of a spectroscopic observations carried from the HCT. But the takeaway point is taking spectroscopic monitoring is a highly expensive process because for one spectrum you have to take at least 1 hour exposure. And if you want to have some 50 epochs, you want to spend 50 hours. It's a very expensive process. An alternative method is what one can think of. The idea is to have tunable filters. So if you have a tunable filters, we can properly put the filter in the line, filter in the nearby continuum. It's in 10 minutes you can get few exposures. Try to do a cross correlation. You will be able to find black hole mass of hundreds of sources, which is one thing is one can very easy to do, and this will be a highly impactful science one can do if you have a tunable filter. Though the filters are expensive, but I think it is worth investing in such a thing. The other item I would like to emphasis is on finding the inner edge of the dust torus. So here the idea is the optical variation is coming from the central engine. It gets reprocessed coming from the torus and coming in IR. So if you have optical and IR simultaneous imager, you can do cross correlation and find the extent of the torus. So these observations are from HCT, but the idea is to have a dual band imager, optical plus IR. So if you have such an imager on a small telescope, these kind of things can be done. So this is the way forward, some possible thoughts. As I told you, polarization variation is one critical thing which we can inspect to pinpoint the correlation between flux and polarization. For spectral variation, the thought is to develop a multi-band imager, or one can go for a 3-band imager or a 7-band imager in the ground concept. As I told you, photometric reverberation is a cheap process compared to what? Compared to spectroscopic reverberation, but it is better to have a tunable filter. Then dual imager for finding the extent of the torus. The one point which I want to take is I read in paper reports that ISRO is coming up with some network of telescopes called the Netra project. So I heard these are some small telescopes, and it is the right time to think very seriously to use those telescopes to do some transient science. Not only AGN, supernova, whatever talks I heard in the morning, all these things can be tackled. But the only thing is, this idea may be crazy, but it's better to network all these small telescopes, particularly the telescopes which ISRO is planning. Because their idea I heard is only to monitor space debris. So there will be ample amount of time to do transient astronomy. The only idea is you have to think properly to come up with a nice backend instrumentation, whether it is imager or spectroscopy. I think everybody has to think seriously in this regard to come up with some plans so that transient astronomy can happen. And for example, I am citing the Steward and Smart's telescopes, which we started this program as a support to Fermi. So now we have telescopes, so we have to think seriously too. So this can be some possible future things for moderate telescope. So I stop here.
So thanks, Karim, for giving us this wonderful tour to agent variability from UPSO to Aries. Okay, so one.
Very good talks, Dalek. But when you are taking us through the journey of AGNs, and you said that in early 2000s, you concluded that radio quasars are not, without jets. But it's just not showing up in the radio, right?
Yes.
So we know that when it will emit radio mostly if you have a radio load, right?
Yes.
So then where are these emissions going? The emission will be going in the, the jet emission will be in the high energy.
Yes. So there are.
But why at that time, why did not you people tie up with any of the X-ray, like 2000 there were X-ray.
X-ray missions were there.
So why didn't you tie up with the X-ray telescopes to pinpoint?
Yes.
See, Harris has a very good, in 2006 or something, he had a very good review on these AGNs. And he was pointing to the fact that many of the high energy emission, even optical emission, can come from the jet. Okay. So one thing I would, so now the accretion disk can also produce X-rays, right?
Yes.
So if it is not a Keplerian disk, it is something other than a Keplerian disk, the accreting matter will also produce lots of X-rays, right? So the challenge now is for both the theoretical and the observers is to differentiate between a converging flow and an expanding flow. Jet is an expanding flow and accretion is a converging flow. So, but what are the spectral and the temporal behavior? Okay, that you can do only with energy observations tied up with
other.
So why didn't you people, when you were sort of leading this, did not arrive at that or did not approach people? Okay, so you got the point, right?
I got it. So
Yeah, I think let's try to make it shorter so that,
as you tell,
This
indirect
got
evidence,
counted his time.
indirect evidence is based on the presence of some hard X-ray tailings some radio frequencies. That is the indirect evidence. But recently, I have been looking into some other sources. You see, even in low luminous AGNs of 10⁴ to 10⁵ solar mass black holes, if you do high resolution observation, the radio of 15 gigahertz or 22 gigahertz, you will be able to pinpoint low power jets. Observation we can find. These things are not known for many sources, but I have been looking at some sources where I have found, but they are known to show hard X-ray variations. Everything is there, but there is no evidence of large scale jets. At 1.4 gigahertz, if you see in the first survey, there's a point source. The same source, if it is observed at 22 gigahertz or 15 gigahertz, we clearly see a core and a water. So this has to be clearly investigated in a sample of low power adequate sources.
Just one point. Now that I'm visiting the Integral Data Science Center in Geneva, and I actually discussed with them and even made a proposal, formal proposal, to exploratory proposal before we could start a full flight, to take a few quasars with the hard X-ray detection because they had just come. But the people are so biased. The committee, they said that we don't believe that these have jets. They do quite well. Although later it has been confirmed. So they did not give time. And there was a lot of pressure on time. This short answer.
okay, one quick question and then.
Yeah, just a quick question. Like you said for polarimetry of these sources. So what is the sensitivity that you require and what is the band that you would prefer?
So here, as of now, the polarization observations available is only on B band. This all studies done from RTL. At least from the Kavlu for 1 or 2 telescopes we attempted. So we have simultaneous many band polarization observed. So if you have 3-4 images, then we'll be able to pinpoint whether there are other components apart from synchrotron, etc. But the problem is how much sensitivity level we don't. It depends on the polarization. Some sources are known to have 10% polarization. Some sources are known to have 3% polarization. For example, when Mercurian photon we attempted, we could not get the source on the water. on the slit in the cover. So what we did, we scanned nearby and we fixed the position where the polarization jumped. So assuming, okay, that is the place where we are pinpointing them. So it's very difficult to tell now. So it depends on what level you want to track. At what percentage level of polarization you want to track.
Okay, so let's thank Stanley.
Yeah, I can only see that, you know, as you can see, this, his PhD thesis, it's called the young generation. He told him young astronomer award, and it was well appreciated, and credit goes to Gopal. I mean, as you say, theoretical, not only observation, but you need to explain it, and Gopal contributed to that.
It's not the selection criteria very well.
I can add.
Very good.
That the young astronomers award has not only gone to Stanley, but he has even gone to his student Pali.
But that's,
So-
I'm highlighting.
So let's continue.
Guru
Yeah.
Shishya Parampara.
So our next speaker is Dr. Haritma Gaur, and she will talk about contribution of 104 centimeter Sampurnanand telescope in optical variability of lasers. So please go ahead.
Good morning, everyone. So today I will talk about the contribution of 1.04 meter Sampurnanand telescope in optical variability studies of lasers.
You have to come this side.
So that you can see the camera is there.
So the outline of my talk is, first I will give a very brief introduction about lasers, then I will summarize the results of optical variability studies which are done on IDV and STV time scales. Some of the results about the spectral energy distribution in optical bands. Then I will talk about the studies of Roma BZ cat newly discovered lasers, and then some future prospects which can be done with 1.04 meter telescope or 1 meter class telescopes like this. Laser, as we know, that it is a radio loud class of AGN, and it is divided into two classes, BLX and flat spectrum radio lasers. They have flux variability across the complete EM spectrum, and there is variable polarization from radio to optical bands, non-thermal radiation, and the main thing is that the jet axis makes an angle of less than 10 degrees to our line of sight. The spectral energy distribution of laser is a double peaked structure. First one peaks at low energies, and second one peaks at high energies. And the classification is like that: if the first one peaks at IR optical at low energies, and if second one peaks up to GV energies, then the class is called low synchrotron frequency peak laser. And if the first one is like at approximately in X-rays, UV X-rays, and second one peaks up to TV energies, then the class is called high synchrotron frequency peak laser. And the emission mechanism probably at low energies is synchrotron, and at high energies it is probably inverse Compton. So here I have shown the spectral energy distribution. So here you can see the same thing, that the low energy part is because of the synchrotron emission, and the high energy part of the city is not well understood, but it can be explained by as arising from the inverse Compton scattering of the same electrons that are producing the synchrotron emission. So if they upscatter the synchrotron photons, then they are called the synchrotron Compton process. And if they are external photons originating in the local environment, then it is called the external Compton emission. So there are a lot of challenges to understand this high emission part. So as I already told, that lasers are variable, and they have been long recognized as variable. Their variability occurs across the whole electromagnetic spectrum. The cause of variability, the basic models which explain the variability, is due to the shock-based jet model, turbulence and relativistic jets, or maybe geometrical effects. So laser variability timescales are divided into three classes. So they are, sorry. So laser variability are divided into three classes. It is of few minutes to less than a day, and it is called intranet variability. And if it is of days to weeks, then short-term variability, STV. So these terminologies I will use in my talk. And if it is of months to years, then it is called long-term variability. So here you can see the typical light curve of a laser and radio band. So they are highly variable in the whole electromagnetic spectrum.
Now I will summarize some of the results that are done using 1.04 meter telescope. So this is the work that I have done in my thesis. So I observed this blazar in many nights using 1.04 meter telescope in order to find out the variability time scales. If I found out the variability time scales, I can consider the size of the emitting region. But unfortunately, I did not find. So here in the left panel, one can see that this is the differential light curve of the blazar with respect to the center star, and this is the star differential magnitude of star 1 and star 2. And I performed the structure function and discrete correlation function. And these are the methods in order to find out the variability time scale. If there is characteristic variability time scales in the light curve, but I did not find out. Now, so these are the IDV results. So these are the work that is done by Aditi Agarwal. And so here you can see, so they observed this BL in R bands, and they found the source was highly variable at that time in 2015. So most of the time, these low synchrotron frequency peak blazars, they are highly variable in optical bands. And this is the work done by Ashwani Pandey. And so they observed from using 1.04 meter Sampurnanand telescope, high synchrotron frequency peak blazar. But you can see that the light curves are approximately flat. They did not find any significant variability. Now I will summarize the results on ITV time scales. So we observed approximately 2 dozen of LSP and HSP blazars in BVRA bands using Sampurnanand telescope. And the results are based on all of these works, which I have summarized here. And then I made this table. So the final result is that we constrain the duty cycle of the various classes of blazars. So in LSPs, we found out that the duty cycle is approximately 52%. For ISPs, and these are the intermediate synchrotron frequency blazars, whose synchrotron peak is in between the low synchrotron and high synchrotron frequency peak blazars. So they have a duty cycle of approximately 35%. And for high synchrotron frequency peak blazar, they are less variable in optical bands, and only 8% of the sources show duty cycle is approximately 8%. So this less detection of IDV in HSP blazars is in agreement with the previous conclusions, which says that these sources are intrinsically less variable in optical bands as compared to the low synchrotron frequency peak blazar. And the possible emission mechanism is due to the differences in the spectral energy distribution of these sources. So here you can see that these LSP sources, they have a peak in the optical bands, and hence the highest energy electrons are available for synchrotron emission in optical bands, and hence they are highly variable in these bands as compared to the HSP sources, which are highly variable in the whose synchrotron peak lies in the X-ray band, and hence they are less variable in optical as compared to the X-ray bands. So these are the results for the IDV studies. Now I will just show some of the results which are being done in short-term variability time scales. So these blazars are observed for like month time scales, and we search for the flux variations, and we also search for the color variations in the blazars in order to find out whether jet-based models can be used to explain the flux variations. So here you can see this is the work by Pandey et al. From 2019. So they observed the HSP blazar on long-term time scales. So the work, the observations are done with Sampurnanand telescope, and this is done by Agarwal et al. 2015. And the source was in flaring state at that time, and they observed it for I think 15 or 13 nights. So they detected clear STV, and they also find out the color variations also. Now, so we also performed the correlated variations between color and magnitude. Here you can see that there is a positive correlation between the color and magnitude, which can be used to see if there is a spectral variability along with the flux variability in the sources. So here you can see that there is a positive correlation, means Bleer and Bretter trend, and most of the VLX we found that they follow Bleer and Bretter trend. However, sometimes the opposite trend is found for the flat spectrum radio blazars, where prominent emission lines are there and where the equation disk plays an important role, but not all of the time. So
some, in our sample, the flat spectrum relative lasers, they mostly shows greater than. So now I will just talk about the study of the spectral energy distribution in optical bands. So here when we just accumulated the data from 1.04 meter telescope and we calculated the spectral energy distribution of lasers in optical band BVRI. So in this small band we can just approximate the power law with approximate SET with the power law, as the band is very narrow. So F nu is directly proportional nu to the power alpha, and from this plot you can see that for LSP lasers, the optical band is in the ascending part of the hump. Therefore, the alpha should be greater than 0.75 to 0.80. However, opposite for the HSP, for HSPs, it is in the ascending part, and for LSPs, it is in the optical band is in the descending part. Therefore, for HSPs, alpha should be less than 0.75, and for LSPs, it should be greater than 0.75 or 0.80. So, in order to find out whether we really got this, we just accumulated the data from the telescope, Sampurnanand telescope, and we calculated the spectral indices for different classes of lasers, and the results are summarized here. So here you can see that these red ones are the HSP sources, where we really found the spectral indices between 0.5 to 1.8, and for the LSP lasers, we find out that alpha is greater than 1, and it is approximately 1.5, and it supports the synchrotron self-content loss-dominated synchrotron emission. Now, I will talk about the work that is done by Kalita et al. 2021 on the optical variability of the newly discovered lasers from the Roma BZ CAT catalog. So here, this Roma BZ CAT catalog is a multi-frequency catalog, and it contains thousands of newly discovered lasers which are never studied for the optical variability studies. So they extracted a sample of 10 sources from the Roma BZ CAT catalog, and they observed them for 20 nights in V and R bands during this period, October 2014 to June 2015, with the Aries telescope. And they found that there was a non-detection of significant IDV in BLX, and in few of the flat spectrum radio lasers, they found flux as well as spectral variability. Now, this is the work that is done in my thesis. So this is the multi-wavelength correlated variability. So this source, Marketian 421, was in a flaring state in 2012. So I observed this source using this Sampurnanand telescope. So this is the optical data, and these multi-wavelength correlated variability is very important, as it is possible to constrain to locate the emitting region, and it can be explained. It can explain within the framework of the existing models, whether SSC or IC, which model is explaining this. So here you can see that this is the observations in optical band, and this is the X-ray observations taken from MAXI. But somehow I missed the flaring event here, and that's why when I cross-correlated them in order to find out whether there is a link between these, the results were not very significant. But yeah, I found a time lag of approximately 10 days. But I could not say much more about them because I missed the flaring event here in the optical bands. But I'm showing this result because such type of studies are very important in lasers, and 1 meter class telescopes has very important role in doing such type of studies. Now this is the same project, similar project as Professor Stalin was talking about, that optical flux and polarization variability of lasers. Lasers are characterized by high degree of optical flux and polarization variability owing to the synchrotron emission. So therefore, and because of the shocking jet model, sometimes we found that there is a positive correlation between flux and polarization. And one important thing is that here you can see that there are polarization angle strings also, which are also shown by Professor Stalin, that along with the gamma ray flaring activities, or sometimes in flaring activities in other bands, there are polarization angle strings in the laser. So the possible emission mechanism is not known, and hence more studies are required. in this direction, and therefore from last 2 to 3 years we are observing few of the blazars using aim-pole, and Kiran Wani is doing this, so the data detection is going on. So we will study the flux and polarization variability studies, and we will see whether there are polarization angle strings also in the type curves. Now I will talk about some of the future prospects with the 1.04 meter telescope. So the first one is the optical project that one can do the observations of Roma BZ CAT catalog, which has thousands of unstudied blazars and whose optical variability properties are not yet known. And second is the optical flux and polarization variability studies, which we are doing right now. And the second big thing is that we can do the simultaneous. So there is a very important goal of these 1 meter class telescopes in doing the simultaneous multi-wavelength projects. And whenever there are multi-wavelength campaigns, big telescopes cannot point to the blazar because they are very costly, their observations are very costly, and hence in such type of studies, always 1 meter class telescopes are very important because they can continuously monitor blazar for a long time. And most of the time, it is required that we need to cross-correlate the multi-frequency data, and long-term observations in optical bands are required, which can be done using 1 meter class telescopes. And when we are constructing the spectral energy distribution, we need the simultaneous data from the gamma ray to the radio bands, and hence optical data is required in such type of studies. So I just want to mention that there is a very important role of Sampurnanand telescope in such projects, and I found out that approximately more than 30 papers which are published using this telescope. And I'm just showing here, this is my final slide. So I'm just showing here the some of the work where this 1 meter class telescope, this Sampurnanand telescope is used for observations. So this is my work where I have used in 2015. I have used this Sampurnanand telescope data in the multi-wavelength campaign. And this is the work done by Hayashida et al. So this was a very big multi-wavelength campaign where this 1 meter Sampurnanand telescope was used. And I found out that approximately more than 30 papers are published using these using Sampurnanand class telescope, and hence it has a very big role in the optical variability studies of this. So I will stop here.
Let's then continue for this. Right. Question?
I'm curious, why do you prefer to call it intraday optical variability and not intra-night optical variability?
Night.
When you actually observe during night.
Yes, that can be done.
Generally, when we do the observation, we do it from multi-station. So simultaneously have data for more than 24 hours a day. So it is better to say it is intraday. So generally for this type of long campaign, I use around 30 telescopes all around the globe. So sometimes we continuously observe one source for 10 days. So it is better to say this idea.
Okay. The idea is
Not only general eighties telescope, but around 30 telescope to continuously monitor, like longitudinal advantage. Taking
I agree, but for each observation, it is intra-night.
Yeah,
So if you add
I'll say this is from this telescope and this is the intranet for Indian telescope and this is for European telescope and this is for American telescope.
Actually, people use both intra-night or intra-day variability.
Okay. And good thing that you said Sampurnanand class radio telescope instead of 1 meter class radio telescope. That's good. That's good. I mean, you are really trying to sell this telescope. Definitely.
Okay, any further question? So is there any effort to do the modeling of this flux and polarization variability again for AGN on this aspect?
It brings me to the same question. I'm listening to the talks. Where are the modeling improvement? You have to talk to the modelers. We are seeing too many light curves.
There are some models actually, but they are mostly non-radio detected objects. So
Are you talking about this, what type of modeling is the Sputnik distribution modeling
no.
or the?
Light curve modeling.
Yeah,
So it's,
this thing is not much improved because with the like 4 hours or 6 hours observations, one can say that it is variable or not, or just one can extract the spectral energy distribution, much cannot say. So most of the time, the most important result is that they can be used for the long-term observations, where the
some efforts, I
big-
think, for long-term monitoring, they have done these two groups.
Big campaign we have done.
Yes,
Almost,
Yeah.
I will say since 2008 I joined, and we have around 30 publication in larger collaboration, and approximately half of them are led by us.
Hmm.
So in that, it is a big collaboration, something like sometimes the smallest group is around 30 or biggest group is around 200 scientists. So we have all type of people. So detailed modeling is done. Yes, certainly, I think that can be done.
Okay, so thanks, Atma. So our next speaker is Professor Humchan. So he will talk about photometric variability of AGN using 1 meter class telescope, a tool to understand the central engine of AGN and estimation of their black hole mass.
I'm looking forward to seeing training from a theoreticians to you. You take care of your guru's reputation.
I will not talk about those kind of.
I'm still waiting for that.
So.
Thanks to Vijesh and LOC and Dipankar to keep actually asking me to come here. So yeah. So today I'm going to talk about photometric variability of AGN using 1 meter class telescope. This is a tool to understand the central engine of AGN and estimation of the black hole mass. So I think I missed to write the memories because busy. I can just say
After the talk, you can write.
So basically, so I was in Aries since 2008 to 2019. So I was lucky to get job very early. Just when I came to India to defend thesis, I got job. So only people wasn't increasing me because I was basically a high resolution spectroscopist. So I have been working on variation of fundamental constants, and a lot of my time just goes to defend the result and discrepancy we have in VLT data and CAC data. So it was a very burning time for me in Europe, and because defending in every conferences. And I just came to India, I just applied here, and fortunately, I was not asking for recommendation. So I got the job, but then I thought I will not, because I got a very prestigious fellowship, Peter Gruber fellowship, so I won't join for 1 year. So I thought they will say, okay, you won't join, we'll cancel it. But fortunately, Professor Ramsagar allowed me to keep in wait. I cannot join even after 1.5 years. Oh, then I thought, okay. ISER was also coming up at that times. So, and then Professor Dipankar told me that if you enjoy mountains, you should stay in mountains. Because I have a little bit liking for teachings, but I miss second Dipankar by few weeks. He might have survived me. That if you enjoy here, you should enjoy, because if you enjoy a place, the creativity will also follow. Gopal Krishna, I also discussed, he was very happy. He was giving me good wishes for my inning at Aries. I hope I have not disappointed him in my 10 years. So only good thing was that whatever comes in between, I used to just take it without thinking. So in one hand, I was just working on 8 and 10 meter class telescopes, and then I was thinking what to do with the 1 meter class telescope. No experience. I have experience of working at VLT, UVS spectrograph with milli-angstrom accuracy in spectroscopy. Then I just with somebody in Paris, where I was doing this Peter Gruber fellowship. And then there was one varying star, varying absorption. I said, oh, that's something I can try. Because Aries will ask me, what do you do with 1 meter class telescope? So then I have experience of working at Sampurnanand. So I used 3-channel photometer at that time. So I went there with a new assistant. Oh my God. Then I tried to struggle throughout the night, break my neck. Star was not coming in the center. So, and nobody for help, nothing. I was alone. In between, I stopped also. 1 or 2, 3 days I tried, but nobody even asked me. Accountability. Nothing comes out of it. So I was surprised because in reality, I was used for 1 hour, within an hour. We can't even change the setting. That was a kind of restrictions. You have to make perfect OBs in the beginning, all those kind of stuff.
Yeah, that's why you got several automation later on. That area is still running.
Oh yeah. So then, okay. So then actually we started this program, and thanks to Gopal Krishna, so he is basically a pioneer in this agent variabilities. So we had a series of discussions, and then many students had joined us. Joined me. Ravi joined very early times. So then I used to have experience in Sampurnanand telescopes. The first project we started was ball quasar variability. Okay, so it was very nice experience. I used to do in the evening time till 9 o'clock, and Ravi after dinner, etc., will come and will take over. So that was very nice stuff. And this student was actually always, I used to train them for a few days, and then they used to train back. It was so very good in catching the stuff. Another interaction I have is in the science center, because whenever we have very good science center, I was in charge of that for long times. So people want to go to 1 meters. I used to convince them, here is 12-inch and there is 8-inch. No, we want to go there. So I used to keep on disturbing the student also that give the time, there is some VIP. So, and I sometimes used to misuse my position of academic committee members and hostel wardens. So, but all the students have got. So that was, in that sense, I have long experience with 1.04 meter telescopes in that sense. I've listed here all of my students except one who worked on cosmology, Priyanka Vedant, she's not here. And all these students have used 1.3 meters and 1.04 meters. 1.04 mainly, what happens sometimes Gopal Krishna will say, oh, this light is not good, we need to read it. Then time is over, we are writing the papers, then we'll ask somebody in 104, give us time. So that's the advantage. So I was saying this advantage in the beginning of the liberty, and this is the advantage of the liberties. And then many faculty were also involved whenever we write these inter variability kind of paper. So these are basically work which was apart from my quasar absorption by spectroscopy, hydrogen variation of fundamental constant, all those kind of stuff. So only I will talk about whatever we've done on the variability. So why, for example, variability? So this is a cartoon where actually Asian structure is shown. This is just a edge-on view where torus is cut here. So these are the broadline region, black hole, accretion gauge, narrowline region, so on and so forth. Different emissions are coming from different regions. And this is basically when you see it from the top. Okay, you see how complicated it is. And another things which I just want to tell you that, for instance, I'm just giving you a small calculation here. That if you have an AGN just at 20 megaparsecs away, okay, so and if this region is 1 to 100 parsecs, so theta angular separation will be something like extremely small, right? For example, if I take 0.1 redshift, or nearby it is like 0.1 arcsecond. If I take 0.1 redshift, it will turn out to be something like 10 to the power minus 6 arcsecond. Neither today nor future facility will be able to resolve this. But I'm talking about such a detailed steps. This is where temporal resolution play very crucial, right? You can measure delays, and you can have different emission regions. You can cross correlate them and try to infer what is actually happening. Try to infer whether these models, whatever have been proposed for various observational reasons, various observational constraints are correct. Okay, so that's where 1.1 meter class telescope play extremely crucial roles because they are economics. They can afford large chunk of times for monitoring. They're simpler to use, and they are also accessible at many places. Many such telescopes are available. That's not the case with 3 to 4 meter class telescopes. Certainly not with like 8 meter class telescopes, which are required for the kind of science I was doing. That's the absorption line spectroscopy. Where absorption line width is extremely narrow. right? So let me just try to tell you, for example, we have a mixture of 1.3 and 1.04 observations. And I just listed out of the publication list which are relevant, which has used data from these two telescopes. These are the 8 publications. And these are the next 8 publications, 16 publications, out of which 4 are MNRS letters, 12 are MNRS papers. Okay. So all my students have different thesis topics, but partly all of them except 1 or 2 students, they have used and got trained in extensively using 1 meter class telescopes, like 1.04 centimeters and 1.3 meters. So I have broadly classified the key science goal, whatever we have addressed here, in these 5 topics. Okay, so I will not discuss all of them, I will just pick one. For instance, there was one project which led to a PhD thesis of Praveen's Internet Optical Variable weak mission and quasars. Key question was, are these weak mission and quasar radioquote counterpart of BLX objects? People were searching for these BLOs since many decades, but there was no success. So this was some very interesting probe using INOV to answer these questions. I will elaborate on this. I will not talk about this. Is a very extensive study done with this telescope. This was for narrow line Cepheid galaxy, as Professor Stelling was also mentioning, that does narrow line Cepheid galaxy detected a different high energy band do they possess jet? And one of the thesis was actually related to aging feedbacks. So we also tried to insert some of the science on those theses, which was mainly basically on spectroscopical studies using the INOV. Does broad observation line ball blazar exist or not? Then, as Sterling mentioned, there is also a project which was started on internight optical variability from intermediate mass black holes. And this paper has appeared, I think, just 2 days back in MNS letters. And probably, I think Christian will be talking about it. This is what which I have listed as the first papers. And then many other kind of study like peculiar blazar, and many are actually still unpublished. The data has been collected. So in the first part, so I will discuss this issue, and I can take question on other topic as well. In the second part, I will discuss what actually we should do. What is the need of a time right now? This 1 meter class observatory should do. So I'm just proposing this Indian Observatory Agent Radiation Mapping Program. That's IR. Okay. For instance, specific question, immediate goal could be: does low mass black hole agent follow the high mass radius luminosity relationship or not? So this is something which can be taken off immediately. So let me just take this one project. Okay, I will go quickly. So now you just see these histograms. This is the histogram taken from SPSS. Forget this reference, adding reference there. This is equivalent width distribution for SPSS quasars in equivalent width big in angstrom. You see here, this seems to be one distribution here. Oh, and there is this kind of another outliers here. And these outliers are actually whatever is shown here in red. But they are radioquote. They are not really BLX objects. So question is that, what is this population all about? So is it that we are missing some new kind of counterparts of BLX in this unification diagrams, which I just mentioned, put here in 2 horizontal graphs based upon radio brightness, and in 3 columns based upon optical line emission property. So that was a quite interesting question, and we changed it to the conclusive level based upon 1 to 2 meter class telescopes, which was actually complemented with polarimetry and spectroscopy observation from 3 by 6 meters. So this was some details about this extensive works, like kind of observations. See, 85 nights of observations. So 10 nights of data from 1.03. and other was listed. Only two cases which are listed here show the convincing variabilities and the probable candidates, which we are also trying to follow with polarization property. So idea was the following: if they are radioquite counterpart of beer-like kind of object, their ionic property should actually more as compared to radioquite, which was not seen on an. And same conclusion we derived based upon the spectroscopic property, based upon the long-term variability, based upon the polarization property. They show polarization not more than 3%. Okay, so conclusion was the following, which I have listed here. So I will not go in details about the conclusions. Conclusion was the following: that this weak emission and population, this new populations, is basically an evolutionary phase of disease. Okay. And I'm very curious to just show something more about it. We taken it up with some Asian fitting. So Dipankar was saying that we need model, etc. So details modeling of SED was done. It is based using optical photometry and IR photometry. And we estimated these various components. Like, for example, I'm more interested about torus, because idea is the following: if they are really evolutionary phases, then their torus is not well developed. And hence I'm expecting their BLR is not well developed. So I cannot have any control of BLR because of various models, ionization model, and number of stuff. Can I do with NIR photometry? We found systematically that they are almost 42% dimmer in IR. And we got very extremely good report from referee that this is what we were looking since the unification schemes. That somebody has told that these torus structure of AGNs and BLR, they're not independent, they're almost continuous. Covering factor of one is directly linked with the covering factor of another. This was the first detail, and I think this comes up soon in few weeks in the archives. Now, I will do quickly this what can be done. So the many things can be done. I think Shalin has summarized many of them in detail. So let me just see what immediately we can. And we have put some effort. I will just rush them, but go through them at Aries here, in fact. And this is the question, and this is basically the motivations part. So now, main idea is the following. So you cannot afford revolution mapping for big sample with bigger telescope. It's very costly, time consuming. And I'm saying that you don't need to spend that much amount of resources on that, because if you have redshifted narrowband filter, you can catch the emission and flux from the redshifted narrowband filters and continuum flux from the broadband. And do the light curve, do cross correlation, do modeling like Javellians. Okay, model this light curve with their existing different variability model in AGNs, and then try to find the best correlations. And then this delay will give you the radius, and if delay will give you the radius, and you can estimate FWH from the spectroscopy, and then only unknown factor is MBH, you can estimate MBH. And I'm giving you motivation here, for example. I'm telling you, this is the parameter space, whatever AGN we know. And how many of them have been revolutionary map is basically these few dots here. Millions of sources, few dots only. And those dots are also very, very biased sample. People have chosen them based upon their success-oriented selection. What we want actually, we really want to know, it should be unbiased sample. Okay, whether it's variable or not, you should have unbiased sample. Then you should draw conclusions. And for example, these are the conclusions drawn based upon this. But do they exist? Do they actually extend to lower energy? Answer is unknown. We don't know. I am saying, you might say, there's a revolution mapping program going on with SPSS. Why this revolution mapping program? What we want to do? Reason is the following. SPSS is doing at high redshift. Their cadence is 1 week, 1.1 weeks. But these low mass black holes, they delay 3 to 4 days, light days. You need to do daily monitoring. Okay, although for short time, 20 days, let's say 1 month at the most. This is where only we can contribute. This is where we can fill that in. Okay, and so otherwise SDSA will not leave you any space for revolution mapping. So this is where only one small telescope can contribute. So idea was basically this kind of stuff. Narrowband filter, don't do spectroscopy. just do narrow band photometric. Only problem is that because of redshift, this emission and shift get shifted. You need either tunable filter or redshift filter. So I think we were lucky to get a sub project of 40 lakhs rupees at Aries when I was at Aries, and we bought these filters. And we have even tried them. We got such a set of filters, and because we have already made a sample, this sample. For this sample, this filter was optimized. And sorry, I don't know where I'm going. I'm going backward or forward.
No, bottom,
You're going.
Oh, bottom. Acha, understand, now understand. Right. So we were lucky to get this proposal, but we were also a bit unlucky. I just know. So then we actually verified, we did various stuff, and then we were mainly working on this kind of work. So I will not go through the calibration and whatever we want to do and how to calibrate them, various stuff like host galaxy contributions, all simulation. We want to do everything first in simulation. Take care of everything. We know what is going to happen, what error is going to come from the host galaxy, and then we go for observation. In fact, we have made a proposal. We have made proposals. So based upon those proposals, so I'm just going for this one. We have also got nights. And these are the nights not only given for this project, they were nights given for other projects, but we have also allotted as 1 hour. And sometimes most of the nights are given bright nights with nobody used for use. So but I think it was a very successful campaign using this NIR narrates and Jim. So main problem actually turned out to be, which is going to my proposal as well, that scheduling is not done actually the way it's required for the project. Scheduling is done basically whatever nights. We don't need 1 night, we need only 1 hour for daily. But they will give us 1 night, 2 nights, continuous. So whatever observation that we will do. So although we have given pride by giving our wise that this day, this hour, this day, that hours in the program proposal, but unfortunately, we didn't actually succeed on that.
What about 21, 22? I don't see that.
21, 22, yeah, we have not. So I think now we are continuing. It's being continued from IIA growth telescopes and 1.3 meters there. And I'm thankful to Professor Dipankar. He has allowed to ship this narrow band filter from here to IIA as well, share the resources. And this is what we want. This is what is our wish list. Okay.
So you don't have those filters here now.
50% are here, 50% are here. Okay. So wish list and then possible action. Okay. So wish list, as I have just now said, if there's time, I can just read them.
Okay, sure.
Okay, statistically large and unbiased. Needs to disappear basically what's exactly happening here. And then long-term monitoring with good cadence. So this can be actually linked with this transient programs. So it's not only that. Then need wide field telescopes. Okay. So it needs to be in multiple locations in the country because the cadence is very important. Detector need to be very sensitive, broadband, as well as redshift narrowband filter sets or tunable filter. Service mode observation is very important. Nobody can go daily to the mountain for 1 hour. Major automation or automations, especially having auto scheduler. Data processing and data archiving center. So this is the wish list for such kind of projects. And then we need to have a national proposal. We need to make call for national proposals for such long time monitoring with 1-2 class telescope. So institute having 1-2 meter class telescope need to spare some amount of time for this kind of national proposal. I'm saying that if we spend 10% time and we are not going to take off time, whatever, we are actually asking for a time when observer close the observatory and go for dinners. That's more than enough for such kind of proposal.
That's not possible. Because some people have their objects at that time.
Never telescope is never closed. Then somebody goes on here.
Santosh Joshi has been very clever. He has started to develop technique to use moon nights. I think to go 1 step further and start developing techniques to use cloud nights.
What I'm saying basically, if you do automations, and our expectation is that at least it's going to be 150% more use of telescope because the observer has freedom. That's good. But we know get tired. I have been sitting in observatory sometime. I used to write e-admin proposal from there, and then I forget to save the image and I have an image lost.
I think this is, yeah, this is the agenda for afternoon.
Yeah, I think we can discuss there,
So, and then.
but certainly possible.
So can
in
I
the-
do
yeah.
two points?
Yes, yes.
Okay. So I think we need to install such thing in major other university as well, because university should not be ignored, because there is going to be astronomy research, and they are someone actually which will produce human resource program for this kind of in future. So we need to create this common data processing center, data archiving, automation, and implementing these algorithm, and then don't keep it only up to one issue. Share them. Okay, it's better to share them. I don't know why people are very hesitant in sharing. So we should share them, because then actually we will have such kind of national project. And this one news also, the site preparation for 1 meter such telescopes at sea residential at speed with this support is also under. Thank you. And
Okay,
this is one example basically. With 1 meter archival telescope, this is a demonstration. Student when they got first degree of application, nothing is coming, nothing is fine. Let's go to the jet here and see fourth publication in MNRS. They have just 3-day cadence. Even then, you can do accretion deceleration, I think. You can do IOD of blizzard. You can in large sample, enormously large sample. Okay, thanks a lot.
Okay, so for a quick question.
A story to be needed to be told here regarding Dr. Hunchal. Initially in 2013-14, when we are adopted into Aries and we were transferred to Divistal, and we are going through the training programs of taking the observation in 1.3 meter telescope, he was the person who unfortunately misses some papers regarding the work requisition. And now the newcomers who are putting their
Log.
Online
work requisition was the proposal and the initiation of this person that we are using e-administration at our end for any requisition that is going currently in other ways and many ways, helping us reducing the paper use. So
Okay, let's thank
for it.
for that.
No, I learned it also from all this procurement and all those stuff. Like this.
From the part.
For a VLTF.
Okay, yeah, a very quick question because
This mapping thing, collaboration mapping thing, you studied here, or do you have collaborations with international people also? They are also doing this kind of mapping at 1 to 2 meter telescope. I am saying it because I had a night in University of Wyoming 1 meter telescope, and the person came, he said, we are doing this mapping thing, can you give us 2 hours? So I just want to know whether you are having.
No, we started it here, then we approached the Beijing people, and we approached the Thailand people. The main problem was basically a lot of our energy and kind of getting waste.
No, but they're using 1 meter, so you can use their.
Oh, yeah. So I think we have.
so the project was initially started long back. It was a long back project.
But it didn't fail. I think 2 students, this type has been completed.
Here, the main problem is the time, getting the time for let's say 2 hours. per day. Okay, let's go.
I'm amazed, just a comment, I'm amazed. All these times are given for AD scientists. You prepare the, time allocation internally. Why it is so that, you couldn't manage to get time? This is amazing, I'm amazed. This time is completely restricted to any scientist.
No, as I heard, the problem was different. So it was like full night allocation instead of 0.2 night.
Availability of the people, you see.
Yes, it's.
I think
Okay, yeah, we will discuss later.
G drive,
Yeah.
my suggestion probably will find a solution.
Yes. Yeah.
We'll have to discuss all this in the afternoon.
Yes. No. So, our next speaker is Krishan Jha. Krishan will talk about internet variability of UV emissions from powerful blazars. This is the last talk before lunch, so let's see.
Identify same instrument, we all want to use and then put them.
See, I will cheat the time allocation committee, they can sit there then. Yeah. Yeah, check it, how way.
Good afternoon, everyone. I am Krishan and I will be presenting the work which we have done. And this work has been published in MNRS letters. And I must say that this work would not be possible without creative thoughts and continuous efforts of Professor Krishnan. So I want to thank him to complete this project for my thesis. And this is also the part of my thesis. So now I start with my talk. Active galactic nuclei are compact region at the center of galaxy that produce very high luminosity that is not directly attributable to star. And the most possible origin is accretion of matter onto spinning supermassive black holes. Now come to the class of agent, that is blazar. Blazars are active galactic nuclei whose radiation is mostly non-thermal and originates from relativistic jet that is roughly directed toward the observer, having angle less than 5 to 10 degrees to the line of sight. Hence, their radiation appears highly Doppler boosted and completely dominates the radiation coming from accretion and post galaxy. The radiation of relativistic jet also induces beaming in the forward direction, and a well-known manifestation of such beaming is flat spectrum and rapid variability of continuum and polarized emission. The flat spectrum radio quasars are identified as quasar subset of blazar with higher power, and their jets show superluminal motion and flux variability from radio to gamma rays on timescale as short as minutes. As in previous talk, Stalin sir has explained in detail that what are the mechanisms that has been proposed on the basis of intra-night optical variability studies. And these studies have richly contributed to understanding the nature of central internet jets of regions. However, there is a total lack of information on the intra-night variability study of ultraviolet emission from quasars. And the primary reason being time-expensive campaigns from space-bound UV telescopes. Although there are UV studies for large agent samples using UV data acquired with galaxies, but those studies have covered only day or longer time scale. Thus, they have probed the accretion risk rather than the jet. Also, these studies are focused on optically selected quasars. So, therefore, to characterize for the first time intra-night UV flux variability of quasars on our light time scale, what we have done, we have selected high-Z blazar having redshift more than 1.5, so that the radiation would correspond to red-spectrum UV emission, and monitor them intra-night in the optical using the telescope available at ARIES, 1.0 meter for Sampurnanand telescope and 1.3 meter Devastal fast optical telescope. Also, from the detailed spectral measurement of spectra of few quasar jets, it has been suggested that a substantial contribution to non-thermal UV synchrotron radiation may arise from a relativistic particle population that is different from the relativistic particle population that emit synchrotron radiation up to near IR and optical frequency. And this inference is based on the spectra of nodes in the kiloparsec scale radio jets of few quasars, where the spectra of radio jets show upturn towards the UV and then smoothly connecting to the X-ray data point, as you can see in the figure. And the confirmation of synchrotron origin of this high energy component was given by Kara et al. On the basis of high polarization of UV emission. Thus, the above two studies support the idea that optical and UV radiation from jets are synchrotron radiation arising from two different populations of relativistic particles. Thus, the purpose of our experiment was to verify the above suggestion by comparing the intra-night flux variability of blazar at red-spectrum UV and optical pairment. And for this, we made basically two samples for this study, and they are distinguished by low and high optical polarization with division taken at polarization equal to 3%. So now how we made our sample? So our first sample of high-Z blazar was made from 5th edition of Brahma PZ catalog, which is a multi-frequency catalog of blazar that lists 3561 sources. Then out of 3561 sources, we selected some sources based on some observational criteria. That is, the shift is greater than 2, brightness in R band less than equal to 17, declination is more than 0, and right ascension is in between 23 R and 17 R. On applying these observational criteria, we found 10 sources, and all of them are FSIQ based on the classification given by Brahma PZ catalog. The one source having RS16R was excluded because of the non-availability of polarization information in the literature. So this source was discarded. So our final sample for this, our final sample consisted of 9 FSIQs having polarization less than 3%. Then we constructed our second sample, high polarization counterpart for the high Z LP FSIQs but such sources are very rare. So keeping in mind the rarity of such sources, we slightly relaxed our sample selection criteria. That is, redshift is greater than 1.5, brightness in R band less than 17.5, and the declination and right ascension criteria we kept the same. So on applying these criteria to Rama busy catalog sources, we found only one source. Therefore, we made our sample from optopolarimetric survey report that consists of 158 pulsars. So out of these 158 pulsars, on applying the relaxed sample selection criteria, we found 6 sources. And one source having RA13R was discarded due to its highly uncertain redshift. So our sample for HPFQ consists of 5 pulsars having optical polarization more than 3%. And the photometric optical monitoring of these 9 LPFSRQs and 5 HPFSRQs was carried out using, as I previously said in my slide, Sampurnanand telescope and sorry, I have mistakenly written here dot. This source has been observed for more than 5 hours continuously in optical band, and each source has been observed 3 times. And median time duration for LPFSRQs and HPFSRQs was 5.3 and 5.8 hours respectively. For the data detection, we used 2 software, IRAP and Taufoot. This is one of the 45 light curves which we have observed for this study. And in these plots, the first 3 panels are the differential light curve of competence star, and subsequent 3 panels are differential light curves of R sources related to this competence star. And the bottom panel is a plot for seeing during the course of monitoring of these sources. So in this source, we can clearly see the variability. So to detect the presence or absence of variability in the differential light curve, we use appetite test, as has been discussed in Goyle et al. 2013 paper. To quantify the variability, we have computed variability amplitude given by Haddad and Wagner in 1996 paper, and the statistical likelihood of detecting a variability in a single 3 to 4 hour session we have estimated INUV DC given by Romero et al. In 1999. So these are the results we have got in our INUV study. So we have found INUV DC of around 30% for LPFSRQ having variability amplitude more than 3%. For this LPFSRQ has a median redshift of around 2.25. And for HPFSRQ having a median redshift of around 2.0, the estimated INUV DC is around 12%, having variability amplitude 3%. In the past, also INUV study has been carried out for FSRQs having LPFSRQs and HPFSRQs, but those FSRQs are located at moderate redshift of around 0.7. So in their INUV study, they have estimated DC of around 10% for LPFSRQs having variability amplitude more than 3%, and for HPFSRQ, they have estimated INUV DC of around 38% having variability amplitude more than 3%. So you can see that the INUV DC for high Z LPFSRQ is very similar to INUV DC of low Z HPFSRQ. So now we have one point to be keep in mind that access DC for high Z LPFSRQ could be even greater if we consider the fact that these sources are heavily biased toward the most luminous agent class. And for several studies, variability is found to be anti-correlate with luminosity, although this anti-correlation has been established only on month or year like time scale. So whether this anti-correlation is significant on internight time scale is unclear in our studies as well. So what can be the possible explanation for high DC of LPFSRQs? One is that some of LPFSRQs could be HFSRQs, but misclassified as LPFSRQs because their observed resttime UV polarization has been diluted due to the thermal UV radiation coming from the axial disk. But this scenario requires observation verification. If some of the members of LPFSRQs are indeed HPFSRQs, then they would show large directional changes of polarization vector for the sample of LPFSRQs having high redshift. Second is near IR polarimetry. because in that case, the emission would correspond to red-spectrum optical, where a separation of polarization due to the thermal accretion is considered as a minor factor. But this high DC for LPFSRQs does not find any support from HPFSRQs because the INOV DC for HPFSRQs in our study was found to be around 12%, and HPFSRQs cannot be misclassified as LPFSRQs because thermal dilution only lower the optical polarization, but HPFSRQs already have polarization more than 3%, which we have taken from the literature. So on the basis of results of LPFSRQs and HPFSRQs, we found that there is no evidence for a stronger intra-night variability of UV emission for high polarization blazars, in contrast to the blazars monitored in the red-spectrum optical, for which a high optical polarization is known to be a powerful pointer to a large intra-night variability. But it is also important to check for any observational biases that might have spuriously led to higher DC for LPFSRQs in comparison to the HPFSRQs. And one such possible source of bias is intrinsic time duration of monitoring, because probability of detecting a variability is known to rise for longer monitoring sessions. But the intrinsic time duration for LPFSRQs and HPFSRQs, we found it is very similar, certainly not more for LPFSRQs. Secondly, the second possible source of bias can be photometric noise polarimeter, which is indicator of photometric sensitivity of monitoring the sessions. But the photometric noise parameter we have found for both the sources almost similar. So we can say that the low DC of HPFSRQs cannot be attributed to more sensitive photometric monitoring of the sources. So what are the conclusion of this study is that if the present finding, that is intra-night variability of red-spectrum UV emission from LPFSRQs does not have a smaller duty cycle in comparison to LPFSRQ is false, that would mean that our sample is too small to be representative of the high risk blazar population, or they are just a case of cosmic variance. Therefore, an independent study is to check this study is desirable, and that can be achieved through intra-night optical monitoring of large, possibly independent sample of high-Z blazars with low and high polarization. And polarization should be preferably in near infrared, as I discussed in previous slide, that in that case, red-spectrum emission will be in optical, whereas separation of polarization due to the thermal radiation is a minor factor. So a confirmation of the present finding that between high luminosity LPFSRQs and HPFSRQs, where LPFSRQs shows a larger duty cycle in comparison to HPFSRQ, would mean opposite polarization dependencies for the intra-night variability of the UV and optical radiation from blazars. The existence of this difference supported the proposal which we discussed in our introductory slide, that synchrotron radiation of blazar jets in the UV or X-ray regime arises from a relativistic particle population, distinct from the one responsible for their synchrotron radiation up to near higher optical frequency. Thank you.
Thanks.
I also want to thank the committee for giving me an opportunity to present my work.
So, any questions? So everybody seems to be preparing for lunch. So, let's go.
Get to Russia, but point is that this is the first time when intra-night variability is being observed or reported in the UV spectrum. There's a significance of this one. That's why it appeared in the letters. But clearly it needs independent samples and possibly larger samples to consolidate these figures. But if the results are correct, subject to the small size sample, then it is very fundamental, because it means that the synchrotron radiation at UV and optical wavelengths is indeed coming from two different populations, as indicated by independent studies of jets, C273.
And it seems that it would be useful to have 1.3 meter NIR imager or NIR polarimeter for future studies. Okay. So with this, we'll end the session and we will go for lunch. So thank you all.
Okay, so there is a small thing.
Okay.
So participants interested in visiting Devasthal
I saw a dot is also appearing by default in slides. So any one of you, if you are interested to visit the vessel, we are arranging vehicle. 3 Innova have already been arranged. So tomorrow we will start at around after
But if
breakfast.
they are not confirmed.
Yeah, please
1
confirm
hour.
by within 1 or 2 hours. And Dr. Sanwal will be visiting. So one vehicle will be from Halwani for you. Yeah. Okay, so we assemble again at 2 o'clock here. Okay.
Already have a visit to the website tomorrow, so will I have to confirm as well?
Yeah. So thank you, Bridget. So in this presentation, I'll be discussing just the overview of the engineering aspects. My colleagues here will follow up with the detailed presentation of each aspect. So this 1 meter telescope, we were discussing about Guru Shishya Parampara. So this has been our biggest guru and a stepping stone for new projects. And when we joined, we didn't have formal engineers here. Some scientists, they volunteer to become the engineers, and other gurus were the instrumentation scientists at Aries, including then director scientists like Dr. Sanwal, Brijesh, Amitesh. So they had ample time for us. We could discuss every aspect of telescope. Then we learned many things from the astronomers, the senior PhD students that time. They could accommodate us in their busy schedule. We sat with them, we observed, we learned about the telescopes. The engineers, of course, we used to discuss and work as a team. We learned many things from the senior scientific technical staff members and engineering staff members. So these were our gurus. And so in brief, we all know the telescope. It's a very, very simple telescope. We can track the sky very accurately, but by just using one induction motor, which is as simple as a motor which is found in our ceiling fans. So it is that simple. So there is a very, very less demand on electronics. There is no electronics required for tracking the sky accurately. Hence, it is very easy to maintain. And as you can see, the entire telescope is manually controlled. Pointing is done manually. Then it is put on tracking. Although it is assisted by AGU for centering the star as well as assisting the guiding of the telescope. Even the sidereal time is mechanically generated. It's just like our analog clock, where there are a set of gear ratios to display hour, minute, and second. And it's also operated by a fixed speed motor, and there's a differential gearing system to generate the RA. It takes a mechanical input from HA, hour angle, and generates the RA. So the mirrors are passively supported. The secondary is fixed. It's only touched when the mirror alignment is done once in every 2 years when coating is done. That's fairly simple system. I'll just give a brief overview of the electrical, optical, and mechanical system. As I said, the details will be taken over by my colleagues. So this is the beautiful sidereal time generator system. It's a mechanical system. There are 3 dials which transmit the second, minute, and hour position to the dials on the display on the console. So this is the logic. Telescope doesn't use electronics. It uses contactor logic mainly for interlocking. to sense the limit switches, to sense the wrong operation of the buttons when a user presses both forward reverse button by mistake together. So it's just a simple contactor logic system operating at 24 volts. So there's a fairly good noise margin. There are big panel of fuses. Every element of the telescope is powered through a fuse. And it's a cartridge fuse. When it fails, one has to go down and replace. Even the students, the observers, they do this. So they know in and out of the telescope in detail, every component of the telescope. Earlier, it utilized vacuum tube amplifiers. Now it has been replaced. And there are different motions in the telescope: smooth motion, set motion, fine motion, tracking motion. Unlike the modern telescopes, where there is one motor called servo motor, which has a huge dynamic range, which can cater 1 arcsecond per second to up to 2 degrees per second. It uses multiple motors. Unlike the new generation telescope, it uses multiple fixed speed induction motors. So it's like switching on the fan. You press the button, the telescope moves at that particular set speed. Then there's a additional, so there are 3 motors per axis and 1 additional motor for tracking for the RA. There's a motor for the sidereal clock, and even the dials are like motors and generators. The position of the telescope is read on dials. So there's a generator on the telescope, which is called the synchro transmitter, and there's a motor on the console, which is called the synchro receiver. So the advantage, it's very, very easy to maintain. Most of the problems are solved using a tester and multimeter by the technical staff. Of course, we use megars and oscilloscope, etc. during detailed characterization. This is one instant which I want to highlight. In 2018, I think the dot motor had failed, azimuth motor, October. And we could only replace after 2 years because there was a huge lead time in manufacturing the motor. It was a complex process to replace it. And when the motor of 1 meter telescope failed, we could replace it in 2 days. One of our technical staff, he took the motor on a scooter to Aldwani, did the rewinding and got it back. It's very, very simple to maintain locally. And same with the displays also, the dials which are used in the telescope. Of course, there are disadvantages, but the advantages and the fast learning curve of the telescope outshines all these disadvantages. It's not very, I mean, it doesn't offer a remote console, but we are working on that to have a SCADA kind of a layer on the telescope. This is the overview of the mechanical system. It has a warm wheel mechanism, so the reduction is huge. The finest motion I can move by just blowing air on the shaft, input shaft. It's very, very high reduction. So the torque and the moment of inertia is greatly reduced. So there is very little wear on the drive mechanism. That's why we could extend the life of the telescope even beyond the lifetime, the theoretical lifetime of the telescope. Warm wheel has a self-locking mechanism, so it can sustain imbalances safely. But of course, it has a large backlash also. We can't have a servo kind of a system with this kind of a warm wheel mechanism. The transmission, as I said, many motors are coupled to a single shaft that uses a complex transmission and centrifugal clutch mechanism. So it's fairly complex. Where the electronics become simple, the mechanism becomes very, very complex. And the acceleration is also controlled mechanically. It uses a pair of springs. So whenever there's a jerk, the spring absorbs the energy and releases it slowly. So there's no jerk on the telescope. For balancing, it has a set of inbuilt weights. And using a lever, one can simply adjust it and change the moment of inertia of the system. But being very large tube, there's a lot of flexure, and there's also a large thermal mass in the system. But there are ways to counteract these. Then there's an optical system. It's a closed RC. We all know that the beam is very slow, so the misalignments creep in very slowly, and it offers a fine sampling, a spatial sampling. So even we can use a larger pixel detector, and we can have a perfect sampling. There are, of course, auxiliary telescopes for finding the star as well as guiding. There's also a telescope for ADC, but I don't think it was used. I don't know whether it was used previously. So there's atmospheric dispersion compensation for that. There's a separate 10-inch telescope, I guess. And there's a dedicated coating plant. So every 2 years, there's a cycle of coating. So advantages of closed tube: the mirrors are normally very clean. There's no dust accumulation. Disadvantage is thermalization. It absorbs a lot of heat and it cannot be cooled down quickly. Access to mirrors is a bit difficult, and the collimation is difficult because you can't easily move the secondary. Of course, there's no feedback control for focus. So over the night, one has to go and continuously focus the telescope. And there is no on-axis guiding. So there's a differential between the guide telescope and the main telescope. But the beauty is it's not controlled by AI or computer. It's controlled completely by a human being. So the intelligence of the human being is used for controlling the telescope. And it requires continuous human intervention. So we learn a lot from this kind of telescope. It's a serious telescope, can do serious science, and it can be completely manually controlled by a human. And due to simplicity, it can be very quickly maintained. Issues can be fixed. Downtime is less, and it has a very steep learning curve. I mean, within few hours of training, one can start observing with this telescope, and it thus is a very good learning platform for both astronomers and engineers. That's why it helped us in the large projects. I'll show that towards the end of the presentation, how it helped us in gearing up for the large projects. So we have done in past some improvements to extend the lifetime of this telescope, and we are also doing some improvements for having a better tracking, pointing, focusing accuracies. But we want to preserve the robustness of the electrical system here. So we have upgraded the electrical system by not changing the design, but we have a provision to add a layer of electronics to have a SCADA kind of a system. You can remotely monitor the parameters of the telescope, but whether it is there or not, the actual telescope will always work. Unlike the modern telescope where the computer fails, you cannot use it. We are evaluating the mechanical wear and tear. Banghiaji and Nandish will describe about this. So they are planning to fabricate small gears for the gearboxes. Thermalization is one aspect. So now we are replacing all the windows with openable windows, but we also have to see the dust issue. We are facing issue of dust accumulation in dot that we have to evaluate carefully. Then there's a desire to have a motorized secondary for easy collimation during alignment that Krishna will be describing. So this is the overall aspects which will be covered by my colleagues now. Thank you.
Thank you, Kumar. So, yeah, question?
Yeah,
yeah. If there are any questions or remarks, we can take right now. Otherwise, during the presentation. Yeah.
So, you said that the telescope still uses induction motor rather than cold motor. So, how do you do the position control using induction motor?
Position control we are doing. We have to monitor the dials. We have to carefully position the telescope and use the finder telescope to center the star.
Just a comment, I was just wondering, so will you also talk about, or any of you, about the data acquisition system or the status update or any future plans?
The instrumentation aspect, Ramakant, we had covered during the first presentation. Data acquisition
was not covered.
Not covered because the two instrument talks were there, one by Jeevan and
Yeah, but because the data acquisition system should be unique to the, so that's my problem, the way that you acquire the data in dot also. See, every separate instruments have their own data acquisition system, and the instrument is taken off the telescope, the computer is also off. So why can't we think about a uniform data acquisition system just to talk to the instrument which you look?
I think that's a good point. We need to discuss that.
I think Kumpal was had some students working on the past data, so she can comment on what kind of format has to be used.
Yeah, so maybe during our next session, we'll discuss about that.
We can take that. Okay, thank you. So now I think next, Mukesh will discuss about electronics and radar aspects. Mukesh.
Yeah. Good afternoon, everyone. Myself Mukesh, and I will be discussing here the upgradation and development work in 104 centimeter on behalf of team.
My God.
No. So here is an overview of my presentation. I will be discussing introduction and then upgradation and development in telescope, as well as in instrument, backend instrument, and then upgradation in support facility, and then maintenance part. And, coming to the introduction, already Kumar we has said that it is a combination of electrical and mechanical system, robust. So its design is robust. So this telescope is operated by this console. Sorry. This console, it's having the push button switches to achieve the array deck motion, and this array deck motion, that is a sleeve set and fine motion, is achieving through AC induction motors, and these are the details of the induction motor. For sleeving, 390 watts three-phase induction motor is being used, and for set 250 watts and fine three-phase 150 watts, and for tracking three-phase induction motor 390 watts, and different speeds of the telescope while in sleeve by pressing sleeve button, we are getting 120 degrees per minute, and then for set 3 degrees per minute, and for fine 10 arc minute per minute. And there is one additional fine motion that we can achieve through a hand pedal, that is 1 arc minute per minute. Now coming to the next slide. Yeah, upgradation and development in telescope. First, array deck panel upgradation. Existing panel is this. Yeah, we have developed array deck panel with the help of modern industrial grade components, and contactor logic has been developed for this. And for sleeve motion, we are giving sleeve motion through VFD drive, Siemens VFD drive, to accelerate and de-accelerate the motion for a smooth operation, and three-phase soft starter has been used for other motion. Now coming to the next slide, that is upgradation in array tracking motor drive and saddle clock. This is a tracking drive, existing tracking drive, and it contains the 3-stage signal generator and the power amplifier. The signal generator has been developed in-house, has been developed with the help of in-house Peak microcontroller, and now the saddle, this previously it was analog saddle drive was using, and it has been replaced with the digital saddle drive. This is a digital saddle drive with Peak microcontroller, and it's having the MOSFET drive and PWM output. It's also having the wireless model to set the speeds. We can set the speed of the drive system. Now coming to the next, that is upgradation of display and operating console part. We have developed the GUI and GUI to operate the telescope. But integration of electronic parts is very difficult with this electrical system of this telescope because of EMI, EMC issues and surge issues. So this is the GUI, and it is developed in the Visual Basic software, and this is the site information part, and this is the position of hour angle and declination. This hour angle and declination has been taken through the encoder. Two encoder has been mounted for this, and this is the telescope control parts. We can operate the telescope through these buttons, and design has been done in a such a way that we can operate the telescope through console as well as through GUI. And this is the block diagram. We have used the in-house peak microcontroller board, six peak microcontroller board. To these 6 microcontroller board has been interfaced through CAN bus, 2 for read the encoder and 2 for actuating the relay, so that we can operate the telescope, and 1 to read the status of the telescope, and 1 is for communication through PC. Now coming to the next, and these are the setups. This is the main communication electronics, main communication microcontroller board. These are the power supply. This is the encoder which has mounted on the hour angle axis. This is the encoder interface card, and this is the relay boards, and control logic has been done for this with the interlocking, safety interlocking, and PCB has been designed for these boards on Cadence Allegro software. Now coming to the next, that is a synchronization part, synchronization of the dome and telescope part, and this is the software, and for this is the block diagram of system. Telescope absolute position is being measured through the multi-ton absolute encoder, and it is then interfaced through the microcontroller board. Then it is operated. It is given to the PC to this GUI. RA deck, telescope's RA deck can be entered here, and through this RA deck, we can calculate the alt azimuth. Since the telescope is a equatorial mount and dome is off-centric, so correction algorithm has been placed to converting this RA deck into alt azimuth. Once RA deck is placed here, we can turn on the track, then it will automatically track the dome. These are the parameters of dome and encoders. Now coming to the next, that is upgradation in the backend instrument. Motorized filter wheel has been developed for CCD imager and MPOL instrument, and there is also motorized filter, motorized system has been developed to rotate the half wave plate for polarimeter, and this filter wheel can be controlled through this GUI. Yeah, this is designed on Python, and this is the block diagram of system. For this system, we have used the reference sensor, homing sensor, and the mouse microcontroller board has been designed, and stepper motor has been used for this. Now coming to the next, that is the support facility. Support facility is very important for the telescope as well as for backend instruments. So electrical power power distribution panel has been developed, fabricated, and it has modern MCB and MCCB components with the indicators, voltage and to indicate the voltage and currents. And then the small instrument lab has been developed. It is a humidity control ESG safe laboratory. It equipped with the ESG safe tables, chairs, and the tools. It will be using in future for to test the instrument, repair and maintain the instrument, and fire control system has been installed for this telescope. These are the this is the control panel, and this is the fire detector and footer. This fire detector and footer is being interfaced through this control panel. I would like to thank Abhijit for this work. Now coming to the last maintenance part, we are regularly doing preventive maintenance for smooth functioning of the telescope. In daytime, we have given this chart to the concerned technical staff. In this chart, we are checking that people are checking motions of telescopes, and then the limits of the telescope, and the dome motion, shutter motions, and then the backend instrument. They are ready in backend instrument for observation, so that observation could be done in the evening time. And the performance of telescope is also scheduled here in monthly basis, and UPS batteries voltage, and we are continuously maintaining a log of UPS battery voltages. So purpose of doing preventive maintenance that in daytime is that if there is any fault, then it could be resolved in daytime only, so that the minimum downtime will be there.
Okay, any questions?
I was just curious. You said dome center and telescope center, they are offset.
Offset.
How much?
I think
No, he mentioned 100%.
Yeah, there is.
No, it is expected, but 1.8
Dome city and optical axis distance is
no. You see, dome center is fixed. I mean, it cannot vary. Telescope center is also fixed.
No, the tube aperture that is offset from the center of the axis.
There is a counterweight and the telescope. So the telescope line of sight will always be off-centered with the center of the dome.
Yes,
That has been taken care of.
yeah, that's what the
No,
point.
that's what. No, range, what is the range?
It's about 1.5 meters.
I wanted to ask something from you.
Yeah.
This upgradation that you talked about, they have already been implemented, is talking for the future.
Some of the upgradation has been implemented, only the display and that controlling part, because of one motor has been, one encoder is damaged. So we have tendered it, but that company has stopped making it. So
Rupesh, why the question has come up, because in your slide, you say existing and upgraded, so it shall not be called existing. If you go back to your original slides.
For people like.
Because, let's go back. Go back. So
yeah,
here
this has been implemented.
but you cannot say existing. Old panel it has to be said.
It is old panel.
That's why the confusion. So that is the old panel, this is the upgraded panel.
Now, second thing, again, out of curiosity. This upgradation is because there is already a newer technology available, or because something went wrong, so you are.
No.
How do you do it?
Yeah, the reason, what is the need for updation? Yeah.
Technology driven. These contractors, if you see here, these are German 1970s contractors.
Our manufacturer.
And they are sleepy sometimes.
Yeah, that is true.
And
If they go bad, means you are gone.
so for a person like me, I have been an end user. Right. For a person like me to appreciate over the last 50 years, what kind of upgradation has been taken place, timeline. That would be very good. People like that.
I think all these upgradations, what they're talking about is last few years.
Yes, recently
Just
we have done.
last couple of years.
So now dome and price. They are.
Yeah, the consultant team has tested.
Hardware and software is tested. But there is some issue in the algorithm. Option correction algorithm. So one need to check for that, then we can. Very soon it will happen. Actually, after Dr. Mahesh left, there is no one.
I think we can discuss further. So any other question or comments?
Please come back. Now the next.
Tickets are cancelled.
Chat said, he missed for 2 weeks.
Okay, I think that's okay. So Mukesh, I had a quick thing. So you said that status of telescope and dome, it's possible to
Yes,
fetch.
yes.
So are we storing it night to night, like time and status? Because sometimes dome obstructs the field.
No,
We want to
currently
know.
the status is that one encoder is damaged
Okay.
for
Okay.
our angle position.
Okay.
So we have tendered it, and but the company has stopped making it.
Okay.
So yeah. So no. So we find alternate of that, and but that company is providing minimum 100 quantity.
Okay.
So we have to find another encoder for that.
Okay. Thanks. Okay. Let us thank Mukesh. We can discuss things later.
Common status can be merged or integrated with the acquisition software. It will be very useful because the archive that we are planning is going to require all of these inputs. Right now, we have to run through a lot of things. These two can cross talk with each other to be very, very useful for us.
Yeah, I think it's a good point. Kuntal pointed out. Telescope, dome, and the all-weather system. This observatory parameter. Even if it is provided to us in a ASCII format, we can merge with the fixed file header and all that.
Maybe I will say later, discuss briefly. Actually, you see, people are launching in space and getting data and all that. We are having on the ground.
Okay, thanks. I think next is Krishna, and he will speak on optical engineering algorithm. Yes. Thank you, sir. Today in this talk, I will be discussing about the 104 meter telescope, 1.04 meter ST primary coating and elemental activity. Of course, this is on behalf of optics section. Presently, we have 3. With this telescope, we have already also take care of the other telescopes also. And especially, mainly, most of the works are set by our seniors. They set the path. We are simply carrying just we are moving forward with this experience, and we are using that into other telescopes also. Like past contributions are from Gupta sir, Pathak, BC Pan, Tyagi ji, Ravaji, Natiram, and others. And also I acknowledge the past and present in charge of the telescope and engineering and technical stuff of mechanical and electrical sections also. Thank you, sir. If I missed anybody, so sorry. Sorry for that.
I think Somen, you're not included.
Yeah, actually, I'm sorry. Actually, yeah. I don't actually.
Medhi, Bimal, I don't.
Bimal, I have mentioned. So whoever I remembered, I took the data and.
So who is in charge in paper is not important. Is what is more important.
Okay, in this talk, I just briefed about the introduction to facility and just recollect the parameters of the telescope. I just brief of the coating plan. Next, I move to the illumination of the primary mirror. In this, I discuss about the unmounting, removal of old clipping, illuminating and remounting, and the reflectivity, present reflectivities, and some alignmental activities, some upgradations activities we have done to the coating plans, some future plans. So coming to the to recollect the Sampurnanand telescope, everybody knows the things. So I just go into the some of the parameters thing with this RC telescope and installed by colleges. So its a primary series is around 1.06 meter. Thickness is around 173 mm. Secondary mirror is around 324 mm. F number is 13 and primary F number is around 3.9 and magnification factor is around 3.25. Field of view is 45 minutes and plate scale is around 50.5 or 7 mm. Coming to the coating plant, it's installed in around 1980s, early 1980s. It is the MS chamber fabricated by Triveni structure since 1978. It works on the physical vapor deposition principle. It actually mainly contains the rotary drive, rotary pump, and two diffusion pumps. Rotary pumps from Edwards and two diffusion pumps supplied by the HHP. At what is with this plant, the 14th primary mirror is being coated frequently since early 1990s. Especially this diffusion pumps are cooled by the circulating the water from the taps. This is a completely
90s, when first time it was quoted.
Sorry. I have some years. Whatever the data, I will show the some date.
97. 97.
Yeah. Okay.
No,
I
you wrote early, so early means I had before 95.
Okay. Okay.
Late.
I have some years, so I
No,
yeah. Okay.
no, it's not early.
Okay. Sir.
Late 90s.
Okay. So this is completely manual plant, operated by the manual. So coming to the illuminating, so it's not a small piece, so you simply put the in the chamber and it's coated. So it has to follow some particular procedure. So initially we have to take the M1 cell from the mirror telescope, and we have to remove the mirror. We have to transport the mirror cell from top floor to ground floor, and we place it on the stands, and we remove the M1 from the cell after removing these passive pads and thing. So after transportation of the M1 from the cell to washing unit, and washing unit to coating chamber. After coating, coating chamber to after coating, we back to again cell and back to the telescope. So these are the completely manual, and with the help of 5 and 2 ton chain pulleys, we do this. So coming to the illuminating the primary, in order to do the fresh coating, we remove initially we have to remove the old coating. For that, we follow the certain procedure. We set up the particular procedure, and this is nowadays we are following the same procedure for all the even 3.6 meter telescope also. So initially we remove the existing dust and all, and after that, after removing the major dust, everything, so we remove the old coating with the help of the 8% QoS soap solution. After that, we completely thorough the inspect the blank for the any residual aluminum thing, and we completely dry it, and after that it is ready for the go to the chamber. Coming to the illuminating, so after the cleaning of the primary and after thorough drying, we inspect the there won't be any dry marks available on the mirror surface. So after that, we assemble this mirror into the this cell, and this cell go to the this chamber lid. After that, we close it the chamber. So before that, we put the aluminum samples over there over the tungsten filaments. So we beat it around, we put around 250 U-shaped aluminum pieces, evacuate the chamber of the level of -5 millibar, and fight the filaments with the high currents. And so in 1 or 2 minutes it will coated. This you see the before coating the mirror and after the coating mirror. So after that, it will go to the like I said that it will go to the mirror cell and back to the primary mirror cell. These are reflectivities almost more than 75% to 90% of the L1 M1 primary, and this is the reflectivity of the secondary. Even after after so many years, it is still it's more than 80% is coming due to its protective coating, and we do the reset to cleaning also. So coming to the alignment activities, after the coating, we while placing in the primary mirror cell, we ensure that mirror is well aligned with the M1 cell mechanically. So because only whenever we remove the telescope, only thing we are changing is the primary mirror and the cell only. So that's why we ensure initially the mirror with the mirror cell, and after it we check the on-sky alignments. We see the in-axis in focus and out focus images. So we ensure the symmetry of the in focus and out focus images. We check the PSF also, and there is no if any final element is required, we try to do it with the secondary. Every time we park the telescope and we go to the secondary, we try to do it, but there is no major scope for the secondary motion. So we, whatever the possibility, we do that. So coming to the upgradation activities, actually actually these are, like I said, in 1980s. So since then I don't know how much time it has upgraded, but recently we completely we bought this is a rotary pump from Redwords. We completely bought the new kit of this pump, and completely removed the each and every part of the thing, and we reassembled, and it was upgraded to increase the life of the pump. And the next thing is we earlier there are some vacuum gauges, the needle analog gauges. Those are not working properly. We completely changed it with the new Penning and Pirani gauges and the digital controllers. We do the health runs with the proper logs also, and we do the in situ cleaning of the primary and secondary. With entering into the tube, and we do the in situ cleaning. Upgradation coating plant side, actually we are planning for the presently is the Tapley water circulated with our taps. There is no with this water, so much water is wasting. So we are planning to put one chiller, at least even not sophisticated. At least we prepare ourselves with the closed tank with the closed lines. We are planning to do that. At least we can save the water. Some electrical panels, actually, like you said, that panels are around 1970s. So we are planning to upgrade those also, and UPS also. Presently, this completely run on the idle. So whenever we do the coating, we operate the generator and we do the coating. So that also some plans are there, and efficient pumps are very old. Presently, though there are no spares are available. So even I contacted HHV also. So they are also not supporting to upgrade it and provide some heaters inside it. So we have to see how we have to go for the next at least 25 years. So in future, means we can also plan you see the complete that activities are carried out by the chain pulleys and the manual thing. So overhead cranes maybe one possibility is there. So next option is in future, if it is required in next 20 years, because existing upgradations are support is not there. It can be upgraded with the new plant also. Telescope side again for alignment purpose, secondary mirror, like Kumar mentioned, some example similar kind of things would be useful for the easy alignment. And overhead cranes of the building permits that overhead cranes also possible for moving the mirror cell to ground floor. Thanks to everyone, to especially my seniors and who are the goals, because you have worked a lot of time compared to us. So thank you, sir.
Thank you, Krishna. Yeah, what is the maximum vacuum that you get in this?
10 to the power -5. I would say,
maybe you can increase the bluer part.
Yeah. Yes, exactly. Actually, we was capacity over. That's why diffusion we are not getting the support for the pumps. Even they are not manufacturing. HHV also they have stopped. So that's it.
And I think you are familiar with 3.6 meter also, because you people are.
Yes, sir. Yes, sir.
So what do you think after operating that? Would you like to have something here or what?
Yes, sir, exactly. I prefer to have at least one plant here.
You have not mentioned anywhere in your presentation.
No, one I mentioned here. Next up is with a new one, right? Yeah.
But I thought you have experience, so you put more emphasis on that, that based on this experience, because it's a magnetron spectrum.
Yes, sir, yes, sir.
So it has certain, I mean, at least I remember through only writing,
Yes.
a certain advantage.
Yeah.
And as you said, it's 10⁻⁵.
Yeah.
And rest of the problem, Gupta ji is here.
Yes, sir, yes, sir. Actually, that's
You can just see, I mean,
Yeah.
because your many other problems will also.
Yes, sir, yes, sir. So exactly, sir. That's if you assure me, I mean, sir, if you plan for next 25 years, I definitely plan to put that
But you
thing.
tell me, if telescope mirror is fine,
Yes, sir.
what he is telling, he is able to do everything,
Okay.
isn't it? I mean, control and unless mechanically, people they say that it's dead.
Yeah.
Why to throw it?
Exactly.
Yeah, I think we can, health of the telescope and life is fine. I think we need to discuss
No,
that.
he's only talking about this is the coating plan,
Yes, sir.
replacement of the coating plan. Next 20 years, he mentions that.
This, I have small question, I don't know whether you would be able to answer that, some other person. Is the coating which is being done here is as good as the factory coating?
Factory is actually that is protective coating, sir. Here it is bare aluminum. Definitely that is very good.
So that would affect the image quality.
No, it won't image quality, sir.
No, theory, the reason is seeing is very poor. It's about generally hardly you get anything better than 1.5 hours.
Yeah, that I know.
So whatever, I mean, it's like effect image consists of optical defects plus atmospheric thing.
Yes.
Plus mechanical if there are anything. So here, this is my understanding. It is strongly dominated by atmospheric turbulence.
Exactly.
Yeah.
Yeah, regarding the protective coating, the advantage is for 10 years, we don't have to recoat. And the reflectivity will
Then
be
how do you decide that it's due for coating, next coating?
reflectivity. It's fair.
So then it would affect your image quality. And
Total sensitivity. Sensitivity
Image quality will not affect,
Yeah.
only the sensitivity will go down.
How far you can go to space?
Yeah, and also to add whatever is said, this non-uniformity, I think Jack can add to that. Non-uniformity in this bare aluminum layer
It will affect.
the image quality at some level,
Yeah.
but there are other factors which will dominate this. So we have
I have
yeah.
one question. You showed the Zimax drawing. So do we have the complete Zimax drawing?
Yes, sir. I prepared a design.
So because there was some discussion about yesterday about, if you want to add on some instruments and all that, so that will affect your, whatever other errors and all that. You can incorporate that in the first level analysis. Or
Yeah, that can be done, sir.
in terms of the image quality and
Yeah, that can be done.
view and all that.
Yeah. At a certain level, actually, we tried also some polarimeter like
that's what
that we tried. Yeah.
Remax was not available. He only.
I recreated the thing, whatever the information available. So I recreated.
But scatter, is there any calculation of scattering?
No, sir, there is no, sir. Because
You
low.
need another software for that, I know.
Yes, sir. Yeah.
So any other comments? Yeah, Professor.
Yeah, almost say last 20 years you have been coating. Is there any, when you after cleaning, do you notice any local defects? Or
So-
you are happy with the cleaning part?
We didn't find any local defects, sir. Yeah.
No,
And we use very diluted chemicals, so we don't.
I mean, if we stop, otherwise, a couple of things I just wanted to compare.
Okay.
Because you see this telescope and then as most of you know, Tobler telescope, they are twin.
Yeah.
And because of frequent, this cleaning and other things, they were in a sense forced to replace the thing. And actually it is not, the material is, it's from Eastern Bloc. So if you could somehow do the protective coating, because frequent coating may, I mean, not only tough, it's not recommended.
Sir, actually for dot coating plant, we have initiated the talk with HHV to upgrade it with protective coating.
Right.
So you'll have a separate workshop on
Yeah,
protective
yes, sir.
coating.
Yeah.
Because it's a
But
very,
workshop
very
will
important.
not solve.
No, but
Actually,
point is,
physical implementation will solve.
because it costs.
It can't many things. It costs, but cost will come once we know what you want.
So that is why the demand has
If
to
you
come.
don't know, and only paperwork is not going to work.
No, just
Okay,
demand
no,
has
actually,
to come.
last month itself, I put a meeting with HHV. By month end, they will submit some proposals.
No, no, it's good.
By my target is by next coating of the 3.6, I am planning to do the
So
protective
I'm
coating.
just giving one example where one primary mirror is already spoiled, it's replaced, but it has not replaced the quality.
Okay.
Because then there are other problems which you are talking about, they will start creeping up.
I think, sir, we are running out of time, so thanks for interacting discussion. Thank you, Krishna. Now I invite Tarun for mechanical related aspects.
No, if you want input, then only then I will
No,
speak.
sir, your input is very important.
No,
And
but
we are-
if it is unpleasant,
Yes, sir.
I don't
Yes,
want
sir.
to speak.
Why do you think it will be unpleasant?
No, duty wants,
No, the chairman wants to keep the time.
Yeah, good afternoon. I'm really thankful to the organizers who gave me this time for presenting mechanical works on this workshop on role of meter class telescopes in modern day astronomy. I'll be presenting on mechanical developments and upgradations for this 104 centimeter Sampurnanand telescope. I am presenting on the behalf of the mechanical team, the present team, the people who have retired. Actually, there is a lot of people who have even retired, and the mechanical team has been associated with the telescope from the starting. It was developed, and I learned from my seniors, and I'm very happy to see all the seniors from whom I have learned so much. And they are here today to guide us again. So yeah, I'll just give a small introduction to in line with the workshop. So that this telescope provides as means for a lot of gathering and investigating emissions from astronomical objects. And with advancement in science and technology, we have seen more and more large telescopes, and we are also associated with now big telescopes. We have 3.6, and we are moving for centimeter participations and so on. But still, this meter class still has a niche, and we have done very important observations, and we have seen through various talks that how important it is. So we cannot leave it like that. And what people are again thinking that to have more years for this telescope. So this Sampurnanand telescope, I would say, has been quite well maintained by Aries, and all the disciplines, all the scientific engineers have been constantly working to make it functional. And this shows that the productive scientific data, we had so many talks, and the scientific and technical development that have the telescope is still in demand. And talk to Ramakantji, and he still says that yes, people are asking for that telescope time. And I'll just list out few mechanical features for the interest. And that equatorial mount you have already seen, and the primary mirror we have 12 axial and 12 radial supports. Secondary mirror is motorized only for focus, and back-end instrument weight we can have up to 150 kg, hemispherical dome 10.5 meter diameter. That Mukesh was showing, they are trying to do synchronization with the telescope. And this dome height we have a 13 meter. We have a 10 wheel assemblies. They are in pairs actually, and the dome is driven with a friction drive. So friction drive also one major improvement we did. I will show you in the coming slide. And then we have a slit opening of 2.4 meter, and this slit motion is through a chain rope and fully mechanism with a motor. Our dome insulation is thermocol and hardboard type, and the hatch opening is 1.85 into 1.7, through which we are doing the aluminizing activity. And for material handling, we had a 2 ton, and we have put one more 5 ton. So coming to the association of mechanical engineering team with the telescope, because I earlier said that telescope and mechanical team have been assisted from the starting. And Sanwalji is the best person who can tell that. And then for this, we have the main association with the telescope instruments in the dome and the illuminizing activities and the maintenance work. So we try to do all these in the telescopes of this 104. So I'll just give you a small flavor of the one instrument that we developed in 2006, and there are actually a lot of development. So I'll just briefly other instruments I'll just touch upon because time doesn't permit. So we did this design, fabrication, and testing of this 2K CCD photometer with the square filters, and we had a motorized filter rotation. And that time, myself and Kumar had joined, and we had this first job for the this 14 telescope for major development. And then this CCD camera and shutter box is the one thing. It is into 3 assemblies actually. Then is the filter disc box where we have a filter disc, and then we have a telescope mounting flange. So if you will just see from here that this instrument was mounted and the main heart was the filter disc. I'll just give few points about the filter disc also. It was a brass disc of diameter 322 mm and was designed for housing these 5 filters. And there are 5 square filters, 76.2 mm each on a PCD of 192. And there was a step cut out in that for 76.4 to put the filter. And the disc was provided with a hose here for this, putting the sensor for sensing the home position. And then filters were held in the slots. Or there was a actually bakelite cover over that, which had a cutout of 75 mm on this same 192 PCD. And this disc was mounted on a keyed shaft, and from there outside there was a spur gear, and we had a pinion which was coupled with the stepper motor, and we have a controller coming through electronics, and we could move there. And it was used for some time when the 2K CCD was functional for the telescope. And coming to the other type of upgrade and development, to give you different flavors. So I will just show you. This we had designed and fabricated the mounting flanges for different CCDs that were being used from time to time, and control housing for the instrument. Also, there was fabrication of different funnels for the CCD, and various worn-out components of the telescope from time to time have been refurbished and replaced, so the telescope life remains there. So one of the example I will show you that this is the friction wheel that I was talking earlier. So it used to wear out every year. Actually, every year one person was running to Delhi and getting it refurbished, and we had some 4 or 5 pairs for this, so that telescope and dome keeps moving. So we developed this into a silicon rubber molded wheel, and this is now working for more than 12 years. It has not been replaced. So that type of things we are thinking of some permanent solution or at least long-term solutions which can work more. And that time myself and Kumar decided to have some dome synchronization, and now this is being also taken up by our next generation, and they have already showed you what they have done. Because it's the earlier thing that we started that time around 2007-8, and then we designed this wheel mechanism and this an encoder, and we tried to put some readings, but the time had come and we had to move to 3.6 and so on, so we could not completed, but now it's in completion. I am happy with this figure side. And further, I will also give you some flavor because last few years I am more involved in dot activities and there. So Nandish with the workshop team, he's leading in charge, and he's doing development for that, and sometimes we have discussions for that. So recently, in few back, they have got this 4K CCD. So for this, they designed the in-house design and development of the filter wheel unit. Here you can see, and it is being mounted on the telescope and regularly used. So 1K to 4K development, also similarly mechanical, electronics, they have moved in parallel, so that the things are being upgraded from time to time. And we have also upgraded this polarimeter filter wheel, and even also I think showed in the slide, I could see that one also. And it's nice, and we have some camera attachments coming up. And apart from the instruments, we have also tools and equipments that we had procured from time to time to meet the needs of our teams, so that because we have now less of manpower and things are getting heavier or bulky and sometimes not being managed by a single person. So for that we have put some trolleys. We have also taken this aerial lift platform. This 2-ton has been further made to 5-ton, and I had discussion with Krishna also, and maybe we'll be moving to motorized cranes like 3.6. The fact is that we are more involved in geostal activities and not able to get time. And limited people are there. And then another field where mechanical people are involved in major activities, the aluminizing. And Krishna has already shown a lot of aluminizing sequence and all those things. So we are at that time we are coordinating with optics section in various aluminizing activities. We are handling major telescope assemblies. Actually, this 14-inch has served as a very good learning platform for us. Actually, when I joined this, and I know Guptaji, and Guptaji also know optics, how sensitively he doesn't allow any mechanical person to touch it, because he thought we had a strong hand and maybe we can break that. So I was always afraid of touching any optics with at least in presence of Guptaji. So what we did is that we made procedures such that we don't have to actually touch it. So, and this learning was so helpful, and we this was the 1 meter telescope, and now we are doing 3.6, and Vijay knows that. And we have just completed the 4th harmonizing, and we don't need now anybody to touch the mirror, and also we can means all indigenize the operations, and we just I can do all the operations through our internal team. I mean, we don't need any outside support, and the procedure are such that we have some checks every. So this learning we got from here. So once we start working on some things that actually are scalable, so we learn things, and then our learnings also become scalable. So we are also giving manpower support in mounting and mounting activities, and we are using tools and pictures also for aluminizing, and aluminizing plant also sometimes needs some adapters and all those things that are being done. So we are also doing a lot of preventive and corrective maintenance activities from time to time to keep it alive, and that is why we are celebrating 50 years also. And we do some preventive and corrective actions for that. So I thank you all for the patient listening, and I also thank all the mechanical team and previous and past and that are along with us in future also, so that this telescope remains maintained, because it would not have been possible actually without their support. Actually, it's a huge work and a lot of mechanical manpower is involved.
Thank
and
you.
Every person is like.
Yeah, thank you, Tarun. And I must mention that whenever Tarun reaches at the site, it's always there's a planning. There are people who reaches site without planning. Both things works. There are pros and cons. But let us thank Tarun for this mechanical. Thank you. Okay, so it's open for some questions, comments on this mechanical aspect. I think, yeah, thank you. Thank you. So I think it's a time for concluding remarks. Kumar.
So I just wanted to highlight the learnings of this session presented by my colleagues. So as I said, it's all the engineering team is not only the engineers, but we have learned several things from the scientists here, starting from a director down to the students, astronomers, etc. And of course, all the engineering, the senior engineers and the scientific and technical staff members. So the first step, what we did was the previous director's initiative was to salvage the optics from the Schmidt, the beacon and satellite tracking camera, and we actually replicated the English equatorial mount for the Schmidt telescope to modernize the telescope and use it for astronomy. Of course, there will be a lot of questions about this, but we are now working on this. ISRO is also interested and they are funding heavily for refurbishing the optics here. This project was initially led by KG Gupta ji and still there in Aries. So we employed all this. There were many limitations here to digitize this telescope. We can't mount encoders, etc., etc. As I said, the dynamic range of motor. So here, one motor controls all the speeds. There are absolute encoders from Heidi 9. So all these learnings, when we applied to build this telescope, it also served as a learning for the modern telescope like 3.6 meter telescope. So it made our job easy to understand the technology used in 3.6. We also developed extensive telescope control software for Schmidt telescope, as Mukesh has shown some of the screens, and the difficulty which is faced when the telescope is not remotely operable. So all those limitations we wanted to eliminate, and whenever we used to learn, so it's a modular software. We step by step we kept adding several modules and made it very complex. It spans across 3 different screens. So hopefully we'll be completing the Schmidt project in another 1 year. There will be having this kind of TCS. Krishna, as he mentioned, we learned several things from the past coating plan, and it helped a lot, Maheshwar would agree, in developing a new coating plan. So this is the conventional cleaning process. Now it's for the huge mirror, this is the platform where the mirror is clean, and the handling techniques here helped us in understanding what kind of tools and tackles are required for the larger telescope. We got good experience with CCDs on 1 meter telescope. We could go ahead and develop a CCD controller system for a first instrument. And this is not just engineering effect, it was led by a scientist, and you can see the hands here. So this chip was assembled by Amitesh. So it's a joint effort by instrument scientists and engineers, and we could successfully develop this 4K CCD camera, and the electronics you see here, it's in-house developed. We bought the controller and customized the controller for this thing, and it's working on a first instrument. Again, the learnings from, as Mukesh has shown, we have developed small automation for the instruments of the Sampurnanand telescope. And with this learning, we could develop a complex controller. It's a multi-axis controller distributed over real-time network, which is used for a first instrument. And you can see the complex software again, like Brijesh said, it has all the features for logging. It interfaces with the telescope, weather station, generates a log of the filter and telescope, etc., which can be integrated into the header. Like this electrical panel, the learnings we had put across, and we had developed the modern UMAG based panel. This is a platform for us to upgrade the modern telescopes. We are now due for upgradation for 1.3 as well as DOT. So we are evaluating the next generation controllers on this platform. So this is identical to the DOT control system panel here. I missed the dome automation here. So Tarun has shown the integration of encoder, etc., and also the dome, how to build a new dome. Those ideas were all derived from the existing dome, and the evaluation of the dome automation system earlier on the Sampurnanand telescope. This is one of the important thing. Weather station. We developed a small weather station for 1 meter. So DOT had come with this integral weather station, which never worked even after replacement. Since we had the know-how, we could quickly build a modern weather station with a sonic anemometer It gives even the wind gust information, hydrovision wind information. This continuously logged. And yeah, thank you. So just a highlight of the learning we will implement successfully.
Okay, thank you, Kumar. So are there further comments, remarks? Okay, let us thank Kumar for second. So I think before we break for the tea, our former optics engineer, Sri KZ Gupta is here, and he wants to share a few words with us.
Just I want to correct actually. The 1 meter mirror was first of all illuminated in 1997. After that, every 2 years, second time 99, third time 2001, fourth time 2003, fifth time 2005. That's all, because there are some figures which are not matching. After that, it's all right, 2011, 2016, and 2020. That's all. Thank you.
Thank you, sir. And let us give a big round of applause for the entire instrumentation and engineering team. Thank you. Let us break for the tea. Yeah, we will assemble at 3:35, maybe 3:35.
I should be there. Yeah. I mean, I request, I told all the students to come also. But you please have your engineering team. present this. Yes.
बीच में ना मिड रहता है ऑडियो बंद हो जाता है मैच अच्छी
चीजें मैंने लिखा है डाउनलोड कर लीजिए
तो 50 साल से ज्यादा सेकेंडरी हो गए दो है
तीसरा भी हो जाएगा
नहीं दो ही चल रहे
ठीक है मैंने वो ठीक है लेकिन आप कह रहे हो छोटा वाला
आप कहाँ करेंगे हम सोफा के साथ है ना
नेक्स्ट टाइम
वैसे छोटा तो वहाँ पे लैपटॉप रख सकते हैं पानी रख सकते हैं थोड़ा पेपर भी रख सकते हैं और वो ब्लॉक भी नहीं करता है ना रूम को पीछे है So you are going to say a few things to start with. How we are this popularity.
So we have this galactic flanges, etc. And now, after learning how we have to import light from the now the lots of agents, everybody will give it some markers. So I felt that you should emphasize separately and photometric separately. Why? Photometric is a basic. It is the whole thing. You get one thing. But maybe we should actually including the trans, etc. We should make a proposal and give it.
मैं तो यही बोल रहा हूँ देखिए मुझे आप सोमेन की बात कर रहे हैं सोमेन क्या किया मुझे पता नहीं मैं अभी जो सोमेन को देखता हूँ उसे तो मुझे लग रहा है कि सोमेन कुछ किया हुआ है टेलीस्कोप के बारे में उसे कुछ मालूम हुआ है he has not learned but that's the difference Marshall is that Marshall is a true person he's paint his pieces by Harish Bhatt he's not an observer he's not a pure observer also Harish Bhatt is completely dependent on outside observation so obviously he didn't have that much of but he learned here right it's a different attitude Yeah, but let the engineers lead it. Engineers lead it, but
Yes.
the scientists have to be attached to it. I can start with you charge and no delivery. अब स्पीड का क्या होगा? They all along some scientists were recharged. What has happened? No drive, no push, nothing.
Because if you have done it, if you remove that, we don't know whether I have a well-defined thing that you guys can within 2 years time we can keep on a separate
ठीक है हमें बैठना है ना महेश ऐसा नहीं चलेगा जूम मीटिंग में बंद करूंगा अभी
But actually, I am coming on that.
Yeah, but you stay here for 2 more days. It's not that you come attend the meeting and go away. So even this is whether it is that, but we will have this.
यार आग में क्यों कीजिए लग रहे हो?
तो मैं तो पहले की बात नहीं कर सकता हूँ, बट मेरे आने के बाद ऑफकोर्स कोविड था, मैं कुछ बोल नहीं पा रहा। नहीं आप ही आके चला जाता है, ऐसा नहीं चलेगी। 3 बार आए कि वो भाग जाने से नहीं चलेगी, आप जगह पे कहीं पे घूम रहे हैं, जो बात है।
Yeah, I think yeah. Yeah. Around the century. Yeah, but you know what it's what. Yeah, right. They don't get the fact.
मैंने तो आपके कमल है देखिए, कौन के नाम लिया मुझे बोलता है, उस पेपर में है, कुछ सिखा है यहाँ से, अभी भी बात करता हूँ तो मुझे पता चलता है कि कुछ सिखा है, he has no clue about how a telescope operates. I also do not know, but the person who knows, I can make out that he knows. What is important?
Hello. 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 Hello.
मैंने अभी सब स्टूडेंट को बुलाया है।
Hello.
And then actually क्या हो रहा है? बोल रहे हो See, students got everything ready made. Automatic data pipeline, automatic data. अरे ये सीखने की जगह है। वो तो space data से आता ही है। So this is the opportunity you have, and once you learn it, so it's something on the people. वैसे सब भाग रहे हैं पेपर के ऊपर, पर वो सब नहीं होते। To establish yourself.
वो डस्टबिन बाहर
is also important. आपके जब नौकरी का जॉब का इंटरव्यू होता है ना, निकल जाता है। 40 पेपर होने के भी वो शॉर्टलिस्ट नहीं होते। कुछ ये पता चलता है कि ऑर्गेनाइजेशन के लिए कोई वैल्यू नहीं है इसका।
आज तो जबरदस्त में डिस्कस चलने वाला है। आज से ये ना जबरदस्त डिस्कस करेंगे। नहीं वो तो रहना है ना, अभी कहाँ जाएंगे? बोल दे ना नेक्स्ट वो करेंगे
अभी जनरेशन में क्या कर रहे थे बताओ।
तो बाहर हो जाएगा। अब तो इसलिए था ना उनको गुस्सा आ गया। कहीं जब कभी मेंशन नहीं था, कभी मेंशन नहीं था। वो ऐसे पूछ के इधर लोगों को पूछ के लोअर साहब क्या बोलेगा उस टाइम हो गया होगा, उस टाइम हो गया होगा। अरे उससे कागज ले लीजिए आप। और क्या गायब है ना, मिलेगा नहीं। मैं मानता हूँ। हाँ मिलेगा तो